Maybe it is something with that year optimization thing. That thing. Maybe in the proof of that during the last year, which he uses for
Just
yeah. Yeah. Yeah.
That is the first part of the lecture of the mini course lecture on random walks on convex bodies by Piyush Srivastava from TIFR Bangalore.
The topic of these two talks is going to be the problem of sampling from convex bodies. So the setup is going to be very similar to what we have been seeing. So I'm going to denote the dimension by n. So K is a convex body, so that means that it contains. We'll always assume that it contains a ball, and in fact, we will assume even more very soon. So, and the goal is to produce a sample from this, which means that so there's the uniform distribution.
Yeah, she did not record, not picking up.
See the YouTube.
No, board. It's not focusing on the board, right?
Oh, right. I think the camera is.
This is focused on the audience.
Yeah, your results correctly, so that
It's like the reaction videos.
exactly.
Then we should get more lively.
It is moving appropriately.
I mean,
Also, I
trend now.
think
Yeah, it is.
What are called reaction videos. This view is somewhat dispiriting. There's us and then there's behind us the
yeah, it's a little Escher painting. Like,
Right there.
No.
wait.
Lights there. In the corner. There is also
Cool. Use. Such that so as stated, it's an easy problem, right? So if I just want to do this, what should I do? Maybe still it's not so easy. So I need to know where the body is. If I knew a little bit, then at least I have no time constraints, that would be fine. So let's say we also assume that this is the two. So P will always be the two ball. It contains the small r radius ball. We'll assume that r equal to 1. So it contains the unit ball. It's contained inside the capital R ball. Now, if I have no time constraints, what should I do? So I just want to produce a sample from some distribution which is small. In fact, I can do perfectly. You keep sampling from the big ball until you hit this, and whenever you hit, you have a perfect sample. So how long does that take? So the obvious thing to do is to do reaction sampling. That actually achieves epsilon equal to 0. Okay, and but the time it takes, the expected time, is exponential in the dimension. the obvious algorithm for doing this takes exponential the dimension of time. So the goal, actual goal, which is always called goal prime, is to do this in time that is, so time should be in n aspect ratio, and ideally log of 1 over epsilon, but sometimes you will be happy even with 1 over epsilon.
Any specific reason for the log 1 over epsilon?
Yeah, so okay, so log of epsilon comes from the following thing. So if you're doing discrete Markov chains, if you get to say 1, so within total variation distance 1/2, just repeat. So if you have full mixing time, so that you just repeat, and you can get log 1 over epsilon for free. So in some sense, if you have a real mixing time result, if you have a random walk and a real, so I come to that, then log 1 over epsilon should come for free. So sometimes in these cases, we will not even have a true mixing result. But
I don't quite understand this first goal there. So produce a sample
yes.
from, so what does it mean? I mean, I'm not sure what it means, the whole thing means.
Yeah, what it means. Okay, so I have a randomized algorithm. So an algorithm that can toss coins. So just like this algorithm, it could toss coins. It could sample from the big ball. Sample from a ball is easy. So that we are assuming like sample from a cube, sample from a ball, those are easy problems.
Yes.
We know how to do them efficiently.
Yes.
And so it's tossing coins, sampling from those. In the end, it is supposed to give me a point with a guarantee that the distribution of the point is close to the uniform distribution on K. This particular algorithm actually gives it from the correct distribution when it stops.
Right.
But it takes a long time.
Okay.
So you're willing to pay there. You're willing to say that I'll be happy with some positive epsilon. And I'll pay for the time that it takes. But I don't want this exponential dependence on the dimension. Only want polynomial. Is the setup fine now? So the setup will be algorithms that are allowed to toss coins. I mean, there's allowed to sample from reasonable distributions, Bernoulli or even it's like Gaussian and things like that. And from that, for using those coins, we are supposed to now produce a sample from this convex body. I have still not said how the convex body is given so far. So, but that is sort of implicit already. So already when we did this algorithm, we assumed something. So what we are given is, we are given this guarantee, and we are given some oracle, which if we give it a point, it will tell us whether the point is in the body or not. That's all. So this has a fancy name. It's called a well guaranteed membership oracle. So membership oracle because it's giving the members, well guaranteed because of these two. So that's going to be the rough set, the general setup for the board.
And this membership oracle, this doesn't cost algorithmically much.
Yes. So the question is, how do you implement the membership oracle? In some cases, that itself might be a complicated algorithmic operation. So, for example, let's think of some natural cases where it's easy. If you have a polytope, then it's easy. Just check the inequalities. Right? So that's one thing to keep in mind. But here we'll always just assume that there is some oracle which only costs us 1 unit. Whenever we call the oracle, we just pay 1 unit of time for that. And we want to minimize the number of calls to the oracle and other operations and get.
So are you allowed to put K into a particular position?
Yeah, I was wondering, like, this is a natural positioning of K that you write here, or you could think of something else, like isotropic position or something?
Yes. Okay, so I'll come to those things
Okay.
later. So yeah, so right now it's K is just some arbitrary body with these, but there could be special positions where it's faster to think. So we'll come to that. But for now, it's just arbitrary K with just these two values, aspect ratio. So this setup is so this problem. I mean, it's a natural question in itself, but it actually gained interest in computer science from because of a different problem that I will not go into. It's volume estimation. So there again the same setup. You have this well guaranteed body. You have the oracle. You want to estimate its volume up to good accuracy. This is one of the few, or not few maybe, but in this setup it's fine. So often there's all these theories of NP hardness and so on. Here actually you can prove without any complex theoretical assumptions. If you just have this oracle access, a deterministic algorithm, an algorithm that cannot make random choices, will fail. It cannot estimate volumes. So any deterministic algorithm that only makes polynomially many calls to a oracle to such a well guaranteed convex, you can construct examples of convex. Actually, the example is also not so complicated. It's just a polytope. Can be made to fail. Like so basically the way the proof goes, it's due to LHS in the 880s. It's basically it'll keep answering some questions, and when the algorithm answers, so after having made some queries, the algorithm will give an answer to the volume query. But the algorithm will have two bodies in mind with very different volumes, for which the answers would have been the same. And as long as the number of queries is small, you can understand. Okay, so the original motivation was this volume estimation problem because deterministic algorithms fail.
When you say deterministic algorithm fails, it means that it doesn't do in polynomial time.
Yeah, any deterministic algorithm that makes only polynomially many queries will not be able to estimate volume to good accuracy. Okay. Yeah. In this setup. So not saying it for a polytope it won't be able to, because polytope is given by a different oracle. You're given a better description. But if you just have access via oracle, and
the query, the kind of query is still the
queries
membership
is only membership, only membership. Yeah. I don't know if you can even
Can you do boundary,
separation.
like is it on the boundary or not, like, or is it just?
No, but boundary doesn't matter.
Oh,
Because
for
it's
the
zero.
volume
Yeah,
thing,
yeah,
it doesn't matter.
And I'm just wondering if the works also if you have separation. Like if you get something outside, maybe it does. I'm not sure. Yeah. So that's the original motivation, and this this was so the first use of random walks on convex bodies as an algorithmic perspective was in for solving this problem, and this was done by Dyer. So like there's a flurry of work from around 89 to 91, and there are many papers which write different people. Yeah.
Can you write a little bit bigger?
Oh, yeah, sure. Yeah. I'll do that. Okay.
Thank you.
From now on, yeah. so around. Yeah. So this actually this paradigm though of like using sampling for volume or integration or the discrete set of counting is slightly older than that, and you start using random walks for this purpose. So it the first one of the first successes of this was to count matchings in graphs. So it's a discrete, very discrete problem, and the first algorithm was actually based on doing a random walk on all matchings in the graph to be able to sample matchings. It's not maybe immediately clear how to go from sample counting, but it's not such a far-fetched fact. I mean, it holds in much more generality. but at least in special cases, it should not be hard to see. I mean, for example, if I want to do matchings, something I could try to do is use sampling to estimate the probability of a particular edge being in the matching. Once I have computed that the probability of that edge, I know like the fraction of all matchings versus the matchings that contain that, and then I can either remove or collapse that edge and go to a smaller graph and compute these fractions, keep multiplying them. If I have good estimates at each level, I can multiply them and get estimate of the count. So this is roughly how the sampling to counting reduction works. Something similar can be done here as well. But I will not go into those reductions. So we will just focus on sampling. In fact, just random walk problem. So the method they approached, the method they used was actually doing a grid walk. So grid the body and do a random walk. We'll actually just look at walks that do not grid the body, just look at do random walks on the body. So and the method, so sampling method was. So there are two steps here. So one is sampling to integration. The second is sampling. On the body. So in this case, it was a gridding of the body. So this is what we will be. So this was the original motivation. Sample from the body because you want to volume computation. And this is in fact one of the major, like many of the advances in this after this paper. So I mentioned many of those. In the rest of the lecture, but they have come. They have been motivated by making the original algorithm more and more efficient. The original running time was like the dimension. The dimension was raised to the power 23 in the original. It was a polynomial, but it was a high degree polynomial. Right now, it can be done in 5 or 4. So it's quite that's gone down by a lot. But just as a sampling problem by itself, and here it's not just sampling. So there is all like so this is goes back to a question in the last. So this sampling actually is done usually after in many of these papers it's often done after a lot of pre-processing. Using rather heavy duty tools. I mean, heavy duty in the sense that they solve heavy duty problems like ellipsoid algorithms. So the body is put into a special positions and like it's modified, like affine transformations are applied to it so that it's in a special position, and only then you start doing the random for the volume computation to make the volume to make the random walk mix faster and to make therefore the volume computation also go fast. And then usually like the reduction I was just describing, for example, the matchings of going from sampling to counting. Here also it will require many samples. Like you will do one sampling for one body, then some other. So usually you want to shoehorn them. So like whatever you have learned while sampling from in the first phase, you want to reuse it in the second phase rather than restart from. So there are many such optimizations that can be done. So all of that I will ignore. So I will not look at this. I will not look at this. I will just assume that I am given the body. I cannot do anything with it. I cannot put it in isotropic position or I cannot use any of these tools. I just start at a point and do a particular do any random walk. Like so, I can look at with different random walks, but I just do one particular random walk and see how quickly it mixes. So that's the question we are thinking about. For different random walks, how fast do they mix? So this is what we do. So any questions so far? So let me actually before getting into formal descriptions, let me actually write down at least one example of a random walk. Called the ball walk, and it does exactly what it's the name says. So you fix some radius delta. Yeah. So let's say fix radius delta. So and the walk is the following. So if your current point is current, so again this turns to this one. So current and take y to be a uniform point in the radius delta and set so this again I don't know the full history of when this was I think analyzed by Lovash and Simonovich. I probably has an older history, but look at the analysis or at least some simplified version of or another unoptimized version of the analysis later on. But the walk should be at least clear. Right? So you're at a point, you draw a ball around it of radius delta, some small radius. This delta has a lot to depend upon it. It can become small. So you go to 0 and then goes to 0. So it's you take a uniformly random point from that ball, you add it to the current point. Now you're at some point. That point may not be in the body. So if it's not in the body, you just declare failure and you stay there. Otherwise, you move to the point. So it is not hard to put that this one that the uniform distribution on the body is reversible. So maybe I'll write down what reversible means also. But it's certainly a stationary distribution. From more like a stronger thing that it's also reversible. It's a stationary distribution for this. So if you start, if xt itself was sampled from the uniform distribution, then xt plus 1 will also be a sample from the uniform distribution. And the question is if this can so if it started at a point, if it can quickly converge to the uniform distribution. So you can ask, so should it do that? Like some appropriate one.
Yeah.
Like
Sure. Why? Yeah.
it should in everybody.
Where? Oh.
Like should it get our goal right of this? So it does not, and for reasons that are like not in general, and for a very simple geometric reason you can just think of. I mean, I can draw a cube also here, but maybe to make it more dramatic, you look at maybe your convex body looks like this, like just this cone at a point, and you are at this point here. It will just take a long time even to move a little bit because mostly it will. So the ball here will mostly lie outside, and you can make this sort of precise. We'll write down the notion. This basically is this picture is a proof that the conductance of the ball walk in general is very small, so it cannot mix fast. We'll write down what conductance means. But it is actually it underlies all the efficient algorithms. All the efficient algorithms, the most efficient algorithms for volume coefficients still do use ball walk or some version of it because the simplest to implement. So it turns out that that's where you start. It's 1 over epsilon to log 1 over epsilon things to come. The problem with this is that this has to do with this starting at one particular point. It was bad. If you started off with a somewhat diffuse distribution, it will work out, and we'll do a proof that it actually does work out. So your starting distribution is not an arbitrarily bad one, but somewhat diffuse. Things will be fine. So this is called a warm start, and a warm start.
So if the body is in an isotropic position, it's okay.
If the body is in isotropic position, is it okay? So it can be made okay in a sense that you can start. Like I don't know if you start at any point, it's okay, but certainly you can then make the starting distribution diffuse enough, and so that works. So that's what people would do in those efficient algorithms. But okay, so one open problem, for example, as far as I know, it's still open, is that if you start this from the center of the body, does the ball walk converge? Like, does it converge in Polymer time? Is still open. There are other walks which are guaranteed to do that. I'll mention 2 of those, but for the ball walk, it's still open.
Yes, so this delta, can you take random? So if you take delta random, will this?
Yes, actually, yeah. So you can do other filtering things also here, and that. So in fact,
can make this faster.
Yes. So that, yeah. So those things. So this just right after the TIFR Kannan paper, around the same time, there's a paper improving it by Lovash and Simonovitz. I mentioned many things from that, and there they do this filtered ball, which is. And that already, I think, got down the runtime to 10 with 10. Okay, so now let's take a slight detour into Markov chain theory. So if that is too slow, I'll skip it, but I'll write down just to make sure. So we'll have to connect all of this to the geometry of the body also, like this mixing. I mean, it's clear from here that the geometry has to play a role. So something about the body has to come in, and so some isoperimetry, etc. So to write down those things, I will just need a little bit of notation. So, but please do let me know if that is too slow, and then. So the thing I want to make formal is this statement that I just said, conductance of. Conductance. Yeah, so the name, I don't know. So, yeah, we'll see. So it's like a discrete version of the Dirichlet form, and it can often, conductance lower bounds can often be moved into lower bounds on the spectral gap. Then we'll see one result which does that. It's like it's sort of like the Cheeger's inequality, like this connection between the conductance and the spectral gap. Yeah, in fact, since I'm from computer science, so far as Cheeger's inequality means exactly that conductance implies spectral gap. That's okay. So I'll use the notation of Lovash and Simonovitz. So this is very nice. I think a earlier version is from 89 or 90, but the final version is 73. So yes, so, I mean, so all the notation and so results are going from this. So we have a Markov chain. So the notation for a Markov chain I'm going to use is that we have this P. I'm going to write things like P8, which I'm sort of thinking of as a probability of going to A. In one step. So this is a Markov. Markov chain is thought of as something like this, and of course the usual conditions have to be there, like for each x it has to be probability distribution on omega. For each a it has to be a measurable function. So all those standard things.
And then omega is any convex.
Yeah, omega. Yeah, oh yeah. Oh, so k is
The next slide.
yeah. Okay. Yeah, okay.
We are so picky.
Yeah, thanks. Okay. So yes, it's a standard Markov chain, the usual definition. So, yeah, for every x is a probability distribution, for every a it's a measurable function, and so on and so on. Okay, so and then so this thing can be seen as an operator both on probability distributions and on functions, right? So by in standard way. So So pi p is sort of like the probability distribution. So if I not pi like nu p. So nu is a probability distribution on k, and I take one step, so it's some distribution. So nu p can be defined. So nu p is in the I will not usually use these things, but just to right. So this so how is this defined? So nu p is just that's the definition. And similarly, pf is the one step average of f. So this is so the function also, and this is so and yes, so yeah, this is just make sure that take page. I'm not really using these corrections. So what I will be using is the notion of ergodic flow, which is just how much mass flows in one step from one step to the other. And yeah, so that so this is. Oh, I'm sorry. Before that, so stationary distribution. So what is the stationary distribution? So I stationary. Start at pi, take one step, you remain at pi. That's the stationary distribution. So there can be many. I mean, in all the things we will look at, there's only one. So okay. So and so now for us, always all the chains will look at the stationary distribution. Or yes, I'll always say ter because there will be only one. It will be this pi k. So I'll always assume that this pi k associated with p. So p will be some mark of chain, which could be the ball walk, something else. But always we will have this as the stationary distribution. So that will always be there. And so ergodic
Equal to pi.
sorry.
Pi p equal to pi.
Yeah. So this is like saying that I sample something from A, and you according to pi. So it's always so. Sample something from A according to pi, then take one step. What's the probability aligned in B? So right like this. So I have a notation for the process. I mean, let me write in a slightly complicated looking fashion. Just I can of course write this pxp, but so that's the flow. And we say the chain is reversible. So so this So really it's saying that if I take I mean, maybe a more transparent way of saying it, which I'll write down immediately, is that if I take the following pair, I sample once from pi, and then I take one step. So I get 2 points, right? X comma y. This is an exchangeable pair. That's exactly it. So X comma y is the same distribution as y comma x.
So why is it called ergodic flow?
Good. I mean, yeah.
It's not important.
Yeah, I mean, the chain is ergodic that it, yeah, I don't really know. It's just yeah, just flow is fine. Yeah. Okay. So really, like if you allow me to write sort of offensive material, then this is saying that that's what the condition is. That's exchangeability. So the ball walk is reversible with respect to this. In fact, and it's also not hard to see that if pi is reversible with respect to p, then pi must be a stationary distribution. So that's an easy consequence. So let me not try to write on, but it follows these. So if reversibility implies stationarity, pi is reversible to p, then pi is also stationary. In fact, that's usually how you construct Markov chains. You construct reversible chains. So there are many standard methods for doing so, like metropolis filter, heat path, Glover. All of these things are standard recipes for constructing chains that are reversible. Constructing chains that which are reversible for a particular pi that you have in mind. So you start with the pi and you construct a chain, and all of these ball walk, etc., can be seen. So ball walk, for example, can be seen in the metropolis. It's proposing a point and rejecting or accepting it based on exactly the metropolis. So in that way, so ball walk is reversible, and so it's also therefore stationary, and all the chains we will look at will always be reversible. They will all be from recipes like this. So they'll always be reversible with respect to pi. So that's
why is it reversible? Because
yeah,
from x to y, it's 1 over the volume of the ball convex intersected with k, right? I mean,
yes,
that's the density.
But there's this pi x. So I also always get confused about exactly this point, but it is. so let's just think about it. So no, there's this. It works out because the probability of staying at x and the probability of staying at y are different.
Oh.
That's it. This like every few weeks I have exactly this question to myself. So there is but this is actually a nice question because there's something called a speedy walk. What is the problem with the ball walk? So this is the picture that I drew here. The problem is that it is not making progress. Like the step is just getting wasted. So why waste those steps? I mean, like just say a condition on going inside. That is not reversible. That has the wrong stationary distribution. But that's speedy. It will move very fast, but it will break things. I mean, but actually that's useful. So like one of the fastest volume estimation algorithms actually does essentially the analysis use this speedy walk.
So what this means if speedy walk means that you
ignore the steps.
Big steps.
No, speedy walk just means that So in the ball walk setup, it just means that I don't count the steps where I did not make progress. So if I landed outside the body, I don't count that step. So or in other words, I'm conditioning on landing inside. But then it's not reversible. The measure has changed, but analyzing it's still useful. So I'll talk of two papers by Kannan, Lovash, and Simonovich. So one of them analyzes that in quite some detail, and that's one of the faster volume estimation algorithms. The other paper is, I think they probably have many more papers also, but these two is the one I will talk. But the other one is the one that they made the KLS conjecture. So that I will come to.
And that is essentially you are intersecting the ball with the set K.
Yes, and then sampling from that.
Then sampling uniformly from that.
And then Manju's objection is yeah. So okay. So what we do? Yes. So ball walk is reversible. So I still not define what conductance is. Let me now define conductance. I think the history here is that it was actually first done in the discrete setup, like in the setup of graphs and random walks there, and but they're all roughly around the same. So these are all papers from, I think, from around 86 to 88. And I'm confused about the order, so I will not. So what is the conductance? So let me first define the conductance of a. Okay, so I already used phi. Psi. So let me define psi of a set S. Or the psi to be the ergodic flow from S to its complement. So the complement is always divided by the mass of. So this is called the conductance of S, of a set S with respect to the chain and the.
What is S?
Oh, S is any set. Measurable set. So this is the conductance of S. And the conductance of the chain itself is the worst possible conductance. You only go up to half because, for obvious reasons. Then it's the worst possible. So it sort of makes sense. It's saying that these are the bottleneck sets. Even if the chain was completely mixed inside, if the conductance is small, the probability that it goes up. So it's exactly that way. So if you think of this, what is it? So if you multiply, you take this pi s here. This is exactly saying that if I sample from X, what's S? So I have completely mixed in S, and then I take a point from that mixed distribution and take one step. Do I land outside S or not? That's the probability. That probability was the conductance. So in fact it's exactly the conditional probability of the division. So starting from sampling from pi, condition on landing in S, the probability of going in one step outside S. That's exactly what the conductance is. So in that sense, these are the low conductance is like a bottleneck. Says that if there are low conductance sets, you should not be mixing fast. Because at least if you start in those sets, you will not go. So and this can be proved easily. So in the sense that you can. So okay, I've not even defined the mixing time, but you can prove that if the conductance is low, then something called the mixing time will be large. Let me now define what the mixing time is. So
Just a question. So this infimum is just that you just need one bad set. It's not sort of measuring.
yeah.
Bad.
Yes. So I'm talking of worst case mixing right now.
Right.
So worst case mixing is about even one bad set is.
Do you have a typical example for this?
Yes, so in discrete, it's easy to come up with examples. So, for example, so if you're just looking at graphs, random walks on graphs.
Yeah.
So one is something like this. So here, so like the picture is bold. So like, so you make a clique. So here's a clique. The clique, and you make another clique here, and connect them by a path. So now this, so you can mix very quickly here. But the conductance of this guy is very small because to go outside, you have to land on this vertex. So let's say, suppose something is there, n vertices here, n vertices here.
But in terms of convex bodies.
Oh yeah, so we'll prove that usually is, I mean, for most random walks, it's okay. So for the ball walk, this like sets like here are examples. But usually the idea is to show that this is large. That's what you want to do.
Okay.
And even in the ball walk, that this is like really like it goes back to your question also. Like yes, I mean this happens, but it's pathological. If you started off with a reasonably diffuse density, it would happen. So yes, so mixing time of P is so let's call it. Yeah, so let's say okay. So yeah, so this is on K. I have to be a bit careful. So let me say that it is absolutely okay. I don't want to say that also because okay. So from any point which is sort of in the inside. So let's say. So let's say. Or let's say for every x, so or even better, let me just define it as the mixing time starting at x. So mixing time starting at x is you start at x and you run these steps of the Markov chain to get the slot. How long do you take to get this distance below? So this distance. So now so one result again that I would not do is that so low conduction. So basically you can prove something of the following kind that so and this I can even do like I mean need not be a point x. I can also define it for a set like uniform distribution of the set. So if so basically mixing time from some set. So this is an informal statement. Is at least 1 over the conductance. So this is not hard to imagine or prove. I mean, is roughly making precise the same statement that I was saying earlier. That if the conductance of a set is small, so if the conductance is small, some set has small conductance. You basically go to that set, and from that set you're not even getting out quickly. So it will take a long time to.
So, but if say K, your convex body is the Euclidean ball,
yeah,
how would S look like?
Oh, but on Euclidean ball, everything will have, so Euclidean ball will not have bad conductance. So it's not a.
But S, how would this optimal S or this?
Oh, the optimal S. Oh, okay. The worst S. So that depends upon the Markov chain. For the ball walk, it should look like I would imagine like you cut off things out close to the boundary, but I don't know.
Okay.
But yeah, I mean, I think the reason people are not doing it is because for the ball walk on the ball, things are fine. So there are no very bad conductance. Yeah. Okay. So that is fine. But what we are interested in on the other side, we want to show that things are mixing fast. This is the so-called the hard. So this is often, at least in computer science, called the easy side of Cheever's inequality. And the hard side is that if the conductance is large, then you are mixing. So if there are no bottlenecks of this kind, then your spectral gap is small and you are mixing fast. So this is what actually was the contribution of these. So they showed in various different settings that if you have large conductance, then the spectral gap of the corresponding random walk is large, and therefore this chain is mixing. Lovash and Simonovitz show that the same thing applies even on the convex body in the convex body setting. So this on right. So that actually same. So the lowest Simonovitz thing. So what the hard side of the same. So the high conductance in the following step. In the following, so I write on the precise statement. So the Lovash and Simonovitz version. So it says the following that if P is reversible by okay, and so it's like mean is being subtracted. Then this is the conductance. So I need to define what this is. So this is a standard thing. So F. So the variance of any function is decaying exponentially, and that rate is like the rate is 2 by conductance, 2 by psi squared. Psi squared by 2. So the higher it is, the higher the conductance is, the faster it's decreasing. It's saying that the spectral gap in some sense is at least this much. So notice that there's a gap, right? This is square and there is no square. So this gap does exist, like the conductance is not a spectral gap, but it is great.
E pi f is f with 1, right? This does not. E pi of f is f in a
yes, f with 1. Yeah. Yeah, and this in fact implies the mixing time result also, just by we assume reversibility. So
I'm sorry, what is E pi F? I lost.
Expectation of F. Yeah, so it's or just to make sure that. So I want to talk about the variance basically of the function. So the reason it's also the variance is because I mean I can. So this reversibility is also another way of saying it. It means that the operator P is set joint with respect to this inner product. And therefore, if we just take 2t here, then it's the variance after t steps. Okay, so and this so this does imply the mixing time also. I will not prove this. I mean, it is again it's some manipulations with Cauchy Schwarz, but it requires so okay. It's not just that. So basically, it's a rounding problem. It's like so essentially you're trying to prove that the spectral gap is large. So you want to say that any vector that I get. So what are these vectors F? These vectors F are sort of orthogonal to the all ones vector. That's the top eigenvector. And so all these F's are here, and so they're all orthogonal. And you want to say that all of them the eigenvalue is small. So for each one of them you want to do that using just the conductance. So basically using the function F, you have to come up with some set S which certifies that, and that's a non-trivial thing. It's sort of in the algorithmic thing. So many spectral algorithms actually are based on doing this, like taking some vector and cutting, like finding a. So this can be reversed also. Like sometimes people also use the other thing of taking a vector and trying to find a set S from it by cutting it based on its entries. Something similar has to be done here also. So you take this F, use that to construct some S's, like by breaking up the body K based on what the values of F are, and then apply the conductance of that to get it. So that's how it goes. But yeah, it's a. For example, this theorem so they used it to solve the matching. So before that there was no known proof of the fast mixing of the chain on matchings, and this is still going by this is still the only known proof.
Clarification, like is that they say T is reversible with respect to pi k is sort of uniform on K. Is that what?
Yes. Yeah, pi k is uniform.
All the integration is with respect to that pi k.
Yes. This. Yeah. Yes, pi is yeah. K is getting yeah. Pi is equal.
Sorry, what did you mean by mixing? You may have said this when you say mixing. What did you mean? What about the mixing time?
Yes. So I haven't yet gone to that. Yeah. So I want to say that this actually implies fast mixing also. It's just a translation of things.
But in some quantitative, when you say fast mixing.
Yes. Yeah. So at exponential rate, the rate being size squared.
Oh, okay.
Yes, I'll just quickly say how the mixing time thing comes. So basically, we've applied to so here is what. So you suppose. So let's say you're starting at some starting distribution mu naught. Okay. So let mu naught be the starting distribution. And this will explain why I was jittering around what's like here. So I will assume that it has density with respect to pi. So suppose that that's an assumption, but it can easily be yeah. So let's assume that it has. And so we want so what we 2 is define this f to be eta 0 minus 1. This is the function f for which we're going to apply that. So this by definition has mean 0. The density of probability distribution. So and then now we just do this. So we look at f. Oh, and let me just write one more thing, which is that there's one fact, and the other fact is that mu pt has density. So this is again a consequence of reversibility. Apply the p on the right, the density. So then I just look at f p 2t. And sorry, what am I writing? So this is not PT, of course, PT of yeah, it's simple. So this is it. So this is by reversibility, or which is the same thing as saying that P is self-adjoint with respect to phi, finite product, and so this is just equal, and for this guy I can apply their inequality. So this is 1 minus I squared and f norm squared. So that is like eta 0 minus 1, the 2 norm. But this thing, because of
2t, applying 2.
Yeah, 2t. And this thing here, because pt of f is pt of eta 0 minus pt of 1. Pt of 1 is just 1. The function 1 doesn't change. It's an eigenvector. So this thing is just the 2 norm of eta t, the density of mu, like the t is time step. So this is just and now we are done. So we get L2 mixing, which is actually somewhat stronger. So we get that eta t minus 1 less than 1 minus I squared by 2. And yeah, because these are this norms to probability distribution, they're monotone in the right direction. So this is the total variation. One, right? But that is exactly the total variation, or at least twice the total variation. So it's decaying exponentially, with the starting thing being this. So that's why I was getting nervous here because yeah, so I didn't want to start from a point which does not have a density, but that's okay. I mean, almost any walk will very quickly produce a density, and then you start from there. A ball walk will produce a density in one step. So we look at some which don't produce a density in one step. So yeah, so now all this setup was to say that the conductance is an important thing. If we can show that the conductance is large, we are done. We get mixing perfect. If this is not, I should say that this is not. So this comment is important. That this is not tight in the sense that the spectral gap may really be like it's saying the spectral gap is at least psi squared by 2, but it may, and it is at most one psi. That so it's there these two bounds, but they differ by a square, and the spectral gap can be anywhere in between. So this loss may be big. Like maybe you prove a conductance. So what will happen here? So if I prove a conductance of something, my mixing time bond will look like 1 over conductance squared, but it might actually be as good as 1 over conductance. This is a lossy method, at least in principle. And yeah, so it's one side is fine. If we get we show the conductance is large, we get the mixing time is so it's at most 1 over conductance squared, but it might also be as good as 1 over conductance. We don't know. Now what goal is to given all this. But this is still about the chain. The chain is still showing up. And we have a convex body in the hand. So we would want to talk about the geometry of the body itself rather than the chain. And so we need to make one more translation. And so that's the next. So any questions?
Just so there is no confusion, you wanted to write the two things in reverse order, that eta t minus 1 L2 square.
Yes.
I don't know why you wrote it that way. By definition, that is the third thing, right?
Yes, yeah. So this is equal to this, which is equal to this.
And so far, convexity is in getting the lower bound for conductivity. So
Yes.
far, there is no.
Yes, so far there is nothing about convexity has been used. This is all general. Okay, so far, no convexity has been used. Oh, yeah, only thing to some extent is the ball walk maybe does not make a lot of sense. The body is not convex, but otherwise. Okay, so now we want to go to lower bound conductors, and this is where the convexity will really play a role. And so now we can forget on the question here. Conductance is important.
Unique equilibrium measure and so on also happen in lots of situations.
Oh, unique equilibrium. So unique equilibrium usually is a very that is quite mild. I think that should happen even with any reason. Like to make it non-unique usually is a pathological thing. So it might not mix quickly, but usually is like my intuition is from the discrete thing. It might go wrong here, but basically I would think that if as long as the body is thick enough, there are no sort of lower dimension things. So it's connected properly for any reasonable thing.
Weakness of the special.
Yeah. Even in the continuous case, I think it should just be like it should be very pathological.
You have singular. These steps are uniform on balls, right?
Yeah. Then as long as the body is sort of thick everywhere. Yeah, and this of course implies uniqueness also. That everything is converging. Okay, so it turns out that this is like the conductance of the ball walk and some other walks also can be related to an isoperimetric inequality for convex bodies, slightly different from the ones we have been seeing in the previous talk. So this one also so again there's a flurry of work in the early 90s. With different parameters, the proof is in the proof. So it starts off with Loas Universe, I think 89, then Applegate Cannon. Then dire field 9. So there's the same isoperimetric equality is better isoperimetric concept. But let me write on the inequality, and then we the inequality says the following. So so S1 is this joint and then assume that for any segment. So let me write in the most general form they have. I'll just explain what is A. So this means I take one point A and one point B in K and just draw the like so one dimensional. In, so, so this distance, let's say, I'll, let me be not certain notation. This can be any norm, so it doesn't matter because these are all just on a line. So you measure the distance here in the same norm as you use this, but it's really just about line. So the norm. So this and t is a parameter. So assume t is something about S1, S2. So you partition this thing, and S1 and S2 are somewhat far. Far in what sense? That if I take any line segment and look at the intersection of that, then on that line segment, the distance between S1 and S2 is at least t times of that segment.
S3 is the rest.
S3 is the rest, yeah. So we want to say that this volume of S3 is large. That's what the isoperimetry now means. And that's what they show. So then so T is in of course 0, 1. So let's just see what he's saying. So let's just look at one corollary of this. So, for example, the diameter of the body in some norm is t, and the set S2 and S3 are separated by distance delta. This gives something like 2 times delta over d. Because on any line, the line's length of the line is at most d, and so that and that's right, and e can be taken to be delta by d. So, right, so and then you get 2 times Q over delta. So if you think of it in so now, so the reason for this, so then we can, so if you take L2 now, you can think in terms of surface areas, and then this is the surface area is like 1 over D. So because you take the limit as delta goes to 0, divide by delta and take the limit as delta goes to 0. So it's like, or actually like 2 over D, and the 2 over D is, as they point out, it's tight. It's tight for a very tall, thin cylinder. So if you take a like there are set, I mean, you just take so you take a tall, thin cylinder and you take cuts parallel to the base. The surface area is like 1 over D. The diameter is the height, and the surface area is 1 over. Like, and like yes, you take S1 and S2 to be the half partition, so you get 2 over the. So so in that sense, it's a tight inequality for if you're doing an arbitrary convex. So is the statement fine? So this is can we stop? So maybe then so since
Continue, yeah.
Maybe since it's lunch is only at 12:30, maybe you can take 5-10 minutes.
Oh, okay. Yeah. So it's again. So I should also say that like okay. So this is tight. So it made, and this is the thing that will be used to prove the whatever conductance thing you can prove for ball. Actually, it will not be conductance. It will be something weaker because we know conductance fails. So the motivation for the KLS conjecture, which also. So what is the KLS conjecture? The KLS conjecture says that if the body is in isotropic position means that let's say the translation doesn't really matter, but let's say you translate it so the mean of the body is 0, and then if you look at the covariance matrix, you just take some points. It's like the covariance matrix of this uniform distribution of the body, that is identity. So if the body is in that position, then there should be no dependence upon the diameter. Should be just constant. So that's the KLS conjecture. Instead of 1 over D, should be 1. The diameter of a body in isotropic position can be quite large. It can be, I think, even n to the 3 by 2 or something. So dimension to the power 3 by 2. But this in it still, right? It should not be 1 over D. Like the. Yeah. I mean, I'm sorry. Yeah.
But you're talking about the same thing.
Yeah. So there should be no dependence on this. It should be a constant. With theta 1 instead of 2 over D. So that's the KLS conjecture. And we have seen in the previous several talks. So it has, of course, there are other related conjectures, the Boolean slicing conjecture and the thin shells. So the KLS conjecture would, okay, I'm not an expert on this, so I might get this wrong, but I think KLS conjecture would imply all of them, including the slicing sort of stuff. And the current best is the work which is also mentioned several times in the workshop is Lehek and Pratap, which shows that it doesn't get to constant, it gets to 1 over log n to the 5 or 5. So 1 over the log of the dimension. Whereas the diameter of isotropic body in isotropic equation can be as bad as n to the 3 by 2. So
yesterday there was some comment about the expected number of, there was a relationship between the slicing problem and this expected number of pieces, was it?
That would imply slicing.
Right. So, right. It wouldn't be, but do you know the KLS conjecture and the relationship between the expected number of?
Oh, so this is KLS is, I think, supposed to be stronger. It implies
than slicing, but that was also stronger than slicing.
Yeah. Oh, that was also. But that one is false. Right?
Yeah. That's well, okay, fine. Sure.
Implies. But KLS also, I thought it now is maybe even 1 over log is Bose's recent thing.
Oh, this is one that also.
Oh, yes, 1 over log.
Yes.
So the power is removed. It's just
Bose. Just log in. Okay.
This, I mean, last year, technically.
Oh, yeah, last year, yeah. A few months ago.
Okay. You see. So I didn't see this.
Yeah. I mean, Yaner just sort of mentioned at the end.
Okay. Oh, so this is after the lecture. That is also that's 2022.
Yeah. And both slicing and
And yeah,
this
so
thing
there-
has
there- so
some
5 is gone.
method that gives in both the log.
So there's no so what is the situation? It's log n. Log n. And there's no power. Okay, so that's the okay. So we will actually see a proof of this modulo the main technical. So there's a one very nice technical tool which looks very innocuous. Then implies this quite easily. Not maybe this we will see it without the two, just T. The easier. And so that is a localization lemma of Lewis and Simonov. So one thing, so if you at least when I read papers by say Patak and Eldan and so on, so they say that the localization lemma and stochastic localization is the same thing. I don't see how, and I mean I just don't understand how. So if you can help me understand how they're the same. But we'll look at the localization lemma and so it is very nice because basically the localization lemma, what it will do is it will transport this problem to a one-dimensional calculus problem. Then it's either true or false. And so if there's sometime I can maybe even write down the statement of localization. Yeah, you'll just write down the statement and then the main anywhere we get some things.
So in this inequality, the kind of the critical case for S1 and S2 is if there are two large caps, right? They are opposite to each other.
So for sphere, I think yes, and for cylinder also. It's,
yeah. And for other convex bodies, not. I mean,
yeah, it's not clear. Yeah, so I mean the proofs don't make it. So okay. So as I write on the localization, it sort of tries to get to the extreme case, but that extreme case is not. It does not look like it doesn't say where the points will. So I'll maybe write on the localization.
Okay.
So then the next one I will present a proof of a different isoperimetric inequality which relates to a different Markov chain. There we thought could not use localization, so we had to do localization by hand. Actually, one referee call it ad hoc localization. so there it's like sort of very more clear. Like, but there it's sort of but that's a different Markov. That's not ball walk at all. It's like it puts a different like geometry on the body and then does it. And there the extreme sets sort of look like they are sort of outside, like very close to the boundary in some animals, that kind of thing. But so there, because so the localization is done by hand, it's easier to figure out. The localization number is sort of non-constructive. I mean, it goes to an extreme case, but that extreme case is not constructed it's sort of this existential. So it says the following. So it's a very generic statement. So it says if G H So this we should just think of as saying indicators of open convex sets. So what is this? This is a Lovash and Simonovitz localization. GX. This is the standard, like the Lebesgue measuring figure. So G and H are functions, they are positive integrals. And they are lower semi-continuous. Then so what is a needle? So the needle is basically two things. One is so So A and B are points in Rn. And by linear, yeah, it need not be 0 at 0. It's important that it's not necessarily 0 at 0. It's a linear function. This is what I mean by needle. The reason it's called needle is because you should think of it as you have a segment A to B, and this at each point in the segment, like the point A plus T times B minus A, you're thinking of a disk of radius L T. So it's like this is A, this is B, this is the point A plus T, B minus A, and this radius is A. So that's the setup. That's the way to think of it. So what does this needle do? So such that on the needle also the function is they have a positivity. It says that if two integrals are simultaneously positive over Rn, then there's a needle on which also the integrals are positive. So this needle, of course, now the distribution has changed. So that's why it's a needle, like it's like with this weighted distribution with this radius. So that's why it's good to think of it like this. It's of course happening all on the line, but the weight is a weight here. So this all, yeah. So we'll see this. This almost immediately reduces this to a one-dimensional problem. And, I mean, the point why, because suppose this fails, then two integral inequalities have to hold. Something has to have large volume and something has to have small volume, which again, and therefore that has to happen on a single dimension. And it also shows something interesting that so there's something more generalist too. You can instead of talking about volumes of sets, you can talk of like the restricted integrals of log concave functions, and the proof doesn't change because here anyway you will be dealing with a log concave function. So the proof these G and H like later on will look like some indicators of these sets, and this thing that the thing you're multiplying is anyway some arbitrary log concave thing, or well, it is not arbitrary, it is log concave, and so somehow the proof remains the same even for the general. I don't know how many enemies I made.
Question.
One is this connection. I mean, this implies that the conductance is large, is it? Or
oh, okay. So what this is, so this implies that something called the F conductance, which means that the conductance is large. If I okay, so the conductance was that you go over all sets. From volume can be really small. Typically, you expect that small sets should have good conductance to be able to get out. But ball walk, maybe that's a problem because of these corners. So actually, what you will show is that something called epsilon conductance, which basically means you only go to the sets of size up to like size at least epsilon. So some fixed amount only go up to that size, and then only for those things you again write on the essentially the same expression, but now divide by maybe the volume minus epsilon. That is large. And that so there is an extension of what I wrote here just for conductance. There is an extension of this lower system proof that we show that if you get S conductance bonds, you can get some, and then you start off with densities are not arbitrary, but whose density, the initial starting density with respect to pi k is bounded by m. Then your running time will be polynomial in that m. So basically, you can't start from like very small things because if the warm, so that's called a warm start. So it's already somewhat diffuse, and then it means getting to warm start requires these. So it's algorithmic too. So if you have to modify the body and to find that those transformations, you might need some optimization looks like. But yeah, but it can be done, and so that's how the volume algorithms actually they do this rounding first. So apply this thing to that. You can get this warm start and then run the. If you don't want to do a warm start, then you need the full conductance. And yeah. So which isoparabolic inequality use depends upon the chain. So this one turns out to be the
one for ball walk.
Ball
And somehow this implies the conductance.
S conductance
bound
for there's this modification.
this modification.
So we will see that, I think. Actually, I had planned to finish that in this lecture.
Questions? So you said that for the ball walk, it is conjectured that if you start at the centroid of the convex body, then it is that gives you the fastest.
No. So okay. So it's not conjectured. It's open whether it mixes in polynomial time. So the question is you start off with the body. Let's say capital R by small r is bounded by a polynomial. So it's the aspect ratio is polynomial. It's not known whether for such a body, if you start from the centroid, the ball walk, whether it will converge in polynomial time. So these results will not be valid because the centroid, if you start from centroid, the density is not even defined. Whereas these things will only let you do things like small, and even if you take some small number of steps, the density is still like exponentially large because it's supported on some very small set. So it's not. But so I don't know what the conjecture would be, whether it should be this way or that. Should probably mix because it seems like a centroid is like basically really deep inside somewhere, like it's like so that this boundary effects
Talking
cannot.
a little bit asymmetric, then the centroid is probably like.
But so some of the asymmetry is also avoided by this aspect ratio thing because it's this capital R by small r is small. You cannot have very thin needles.
Yeah.
Any further questions? If not, then let us thank Piyush again. It seems there's going to be a conference photo.
Yeah, make just again some announcements. There'll be a conference photo in the coffee break in the afternoon. And then about the excursion tomorrow, so I'll send out an email. So we start at 9 from TIFR camp. At 9:30, there will be a pickup at CVH. Okay, and other details. And in IIC, there will be only at CVH. So because some people get in at the other gates or so, but please be at CVH by 9:30. And from here at 9 o'clock. The other things will be in email. And even if you have not signed up, just reply to us and I think we can accommodate a few more.
So these are, I mean, like in particular, I mean, so these are compact supported, so fine.
that we are little.
Then some limiting. So if G and H put a compact support, you can just take the union of this. Or like just take a large. He's okay. He can call him some network sign.
Just get to here. Yeah, this is the lower is open.
Whereas someone can as the first.
Yeah, I agree.
People
But you
are
have
very
to
finicky. I said, you visit a place, you know how best to.
exactly, yeah. It's totally dependent on what you want, where you want to apply, where you want.
For that, you have to visit and figure out, how
What
best
their
you can
priorities are.
present yourself.
Whatever.
Not at the moment, but it matters at some.
Hiring, yeah. ISC, for example, I don't know what the factors anymore.
But you know.
I don't know. Rajesh, that's all. That's the best I can do. It is. Good kid. In the first day, sorry. I thought you were going to leave. I was not. It's far. Yeah, weekdays I can't. Yeah. Teaching, I mean, semester has started. Oh, okay.
Oh, thanks. Thank you.
লোকজন আপলোড করছে। আচ্ছা আরো আইসিটিএস এর ক্যামেরা গুলো আরো বেটার। হ্যাঁ 12 লাখ টাকা চলে গেছে। কাজের নাই। এটা মনে হয় ডিটেক্ট করার চেষ্টা হচ্ছে কোথা থেকে আওয়াজ আসছে। একটু বেশি হয়ে গেছে মনে হয়। একটু কাছে লাগাতে পারলে মনে হয় ভালো হতো। ওইখানটা লাগাতে হবে। পরে ইয়েটাতে। পরেরটা মনে হয় লাগানো যাবে না কারণ প্রদীপ কার্ডটাকে আড়াল করে দেবে। স্ক্রু দিয়ে আটকে সাইডের দিকে বলছিস তাহলে effective হবে। মনে হয় 6টা বোর্ড কভার না করে 4টে বোর্ড কভার খুব ঠিকঠাক হবে সেটাই ভালো নয় একটা চাপের ব্যাপার না লোককে বলে দেওয়া হবে বলছিস বাট স্টিল তুমি রেকর্ডিং করে পড়াই যাচ্ছে না এদিকে। হ্যাঁ হ্যাঁ আমাকে বলছিল পুরোপুরি ফলো করলে আলাদা ব্যাপার ফলো করলে আর কথা শুনে বোঝা যাচ্ছে আর নয়তো বোঝা মুশকিল পড়ে যাবো এখন প্রচুর ভিড় হবে তো নেই দেখছি বাইরে পাঠাচ্ছে তাই কাজ ছিল গেছিলাম বুঝতে পারবে
the slide. Can you switch on? Actually, my is a there is a point in
We miss your lecture. Subros.
Oh, you are going, okay. Yes, so 4 weeks.
Yes, sir.
How long are you there? You are going for 3 weeks. Oh. No, other people also.
The Philip
Ah. He was there. But he is coming tomorrow. He was there whole of last week. Convex is but more complex. He has class in
Yeah.
Because I have problems with my.
Go for the TIFR. What about that?
Yeah. Some people, they also said they were going. How are you going to do? It's okay. Send to the Shrikant.
Yeah.
Already came. Please for your.
We have to reimburse.
Look at.
How do I
What are you taking?
Fix it. Miscellaneous. Miscellaneous.
Repeating the topic from last week.
Some. Shrikant's number randomly show.
Yeah. Is there something to connect? Yeah. Hi, Shrikar. So? Hello, can you hear me?
Yes, Shrikant, we can hear you.
Yeah. Start Zoom on your laptop,
Okay.
and there is once you log in, you'll get share screen option.
Next second, Rukman. So I have to sign in.
Next one.
Shrikant, do I have to sign in?
Yeah. Sign into your Zoom.
Okay.
Sign into your Zoom,
Okay.
and you'll see one share screen option. Adi, on the touch panel, click share screen.
Urvi, is this yours?
Oh, yeah.
Oh, that's it.
Very nice.
Online payment, it's not accepted.
Yeah. If you have. X.
Oh, no, even function. I mean,
No,
that's
linear
fine.
combinations. Linear combinations, but no, if you want to approximate X, you must approximate the square root X square polynomial. Square root X minus P of X is less than epsilon. That means X.
Subhajit, can you log into Zoom?
Yeah. The meeting code क्या है?
So that's an odd function.
Yeah.
No, you don't have to join the meeting, Shrikar.
Password. But it's asking for meeting password.
Password is 46.
46.
Adi, are you listening? Adi, don't join through meeting. Share screen option comes on the
as soon as he log into his Zoom account.
Shrikant, it is asking for
sorry.
sorry, even after share screen, even after the share screen, there is another page right next to it. Yeah, I am in now. Yes. Can you see Shrikant?
Yes.
It's a real analysis.
Right.
All of those are, if you just have a
Limit to some sparse or whatever. Yeah. But the
Mine. No, it's not mine. Oh, this is yours. I thought it was mine.
Convex geometry and complexity. Wow.
I think Yogesh had something more.
What is his objection?
Nothing. I think he said it's a strange name. That's what you said. Strange short.
What is the problem?
It's not really problem. No, I think it's not a problem.
Problems in
Get a job. Spell something.
Puranic. Puranic.
That would have been acceptable. Okay, so let's start our afternoon session. And the first speaker is Shrika Lama. We'll talk about limit theorems for geometric functionals of random fields.
Thank you to the organizers for giving me this platform. So I won't be presenting anything new, which is a little disappointing for all those who have already heard this talk several times. But for those who are seeing me for the first time, it might be something which might be of interest to you. So without much let's start. So I'll start with very basic definition of what a random field basically means. It's not something which is very fancy. It is just a simple random variable So if you are aware of random variable, think of now random functions. So random variable is a real valued random object. Random function is a functional valued random object. So, and then clearly, if you are talking about randomness, then you have to have ensured measurability conditions. So that is a measurability condition over there. And then this is a map. So typically, if you take any parameter space T in RD, you can take a box, you can take a sphere, you can take any manifold, and then you can define a random field on this parameter space T by defining these random functions. So these are the random functions which will be calling random field. Of course, the most simple example we can think of a random field is a random vector. A random vector is basically a random field defined in a parameter space, which is just the index set 1, 2, 3, 4, all the way to the size of the random vector. If there are any questions anytime, please just stop me because there are several small technical things which I have kind of brushed aside. So if you are interested in knowing, just let me know and I'll try to explain. The kind of geometry that I would be interested in, which relates to random fields, is basically these kind of sets which are called excursion sets. So think of just real line and take a process. Think of a process. So capital T is basically an interval, and RD, instead of RD, think of just a real line. And so now you have an interval, and you are looking at random functions defined on this particular interval. An excursion is basically part of the parameter space wherein the process takes value higher than a threshold. So that is precisely the generalized version of this excursion set that I just defined on an interval. So these are basically all those points on the parameter space where the random function takes a value higher than a fixed threshold. So your threshold can be any value of your choice, but typically in random geometry, the value of the threshold matters a lot. In fact, Kaushik and his student and Manju, they work on different types of these excursion sets wherein the value of U actually matters a lot, wherein U is 0, U is not 0, all those things actually they matter a lot. And then, of course, this set is a random subset of the parameter space. So I don't need to really say that out loud. But then now the kind of question that I'm interested in is, what are the geometric properties of this excursion set? So when I say what are the geometric properties of an excursion set, I have to say what kind of geometric properties. So a natural question of interest is, how big is a random set? So now this question is a little ill-posed in the sense that if I have two of these sets, which one is bigger? Okay, so to me it looks like that maybe the blue set is a bit bigger than the orange set. But if I think of this as volume, the orange set actually has a bit more volume than the blue set. So this question has to be made a little more precise in the sense of what exactly do I mean by bigness. So we'll try to peel off the layers of this question by trying to make this question is a little more precise, mathematically speaking. And one of the questions that we can very directly ask is, what is the volume of this random set? Another question that we can ask is, what is the unit four-dimensional surface area of this particular random set? In this particular case, this is just the circumference. In higher dimensions, one might have surface area, diameters, and lower dimensional other measures. And that is precisely what we would be interested in. And this leads up to something called Lipschitz-Limit curvatures or Minkowski functionals. So this is where I'll go a little slow, and please stop me if you have any questions. So you consider, so I'm just going to define what exactly are these Lipschitz-Limit curvatures. They have actually already been seen in this series. and Elizabeth talked about them, and they appeared in the Steiner's formula. And this is how I would also define them. So if you consider polygon N as a collection of all polyconvex sets in Rn, this particular collection actually becomes a lattice, has a lattice structure. Now this polyconvex, so what is a polyconvex set? Is basically a finite unit of convex sets. Then the kth dimensional or the kth Lipschitz-Killing curvature is basically that number which is unique up to a multiplicative constant, rigid motion invariant, finitely additive, subfunctional, which satisfies this homogeneity property. That is, if you inflate the set by a factor alpha, then the homogeneity, the k, which is a dimension, so to say, comes out in the as a factor, and you see alpha to the power of k in front of the k of the set A. This is to begin with, it may give you some sort of an idea of what exactly these Lipschitz-Killing curvatures can mean. You can imagine that if you have a ball and you inflate or you just factor it, like multiply the set by a factor of, let's say, alpha, the volume actually increases, or rather factors by the same constant, alpha to the power of the dimension. So volume clearly is kind of something which fits in this bill, and indeed volume is a Lipschitz-Killing curvature. In general, if you take any n-dimensional polyconvex set A, there exists n plus 1. So if you have n-dimensional object, there are n plus 1 such numbers which are associated to that particular set A, and these numbers are such that the zeroth Lipschitz-Killing curvature is a Euler-Poincare characteristic. Now this is something again that many of us are familiar with. In differential geometry, we have seen Euler-Poincare characteristic is basically the integral of the Gauss curvature. So this is something we already know. In fact, even if you do not have a very smooth structure, you can still talk about Euler-Poincare characteristic because it's a very nice topological invariant. So you can actually talk about Euler-Poincare characteristic in a very general setting. Now Ln, now notice that this n is the same n as the dimension of the set A. This is the n-dimensional Hausdorff measure, so it is actually the volume. What about the other LKCs which are in the middle between 0 and n? So they have a bit of a strange interpretation in the sense that there is no direct way I can explain what exactly do they mean, but they are measuring some sort of a, so LK is measuring some sort of a k-dimensional measure or k-dimensional volume, so to say, of the set A. Okay. Yes.
So for the other k, it's not the Hausdorff measure.
It is not the Hausdorff measure because which Hausdorff measure of which set? The set A. So and then if you are talking about sections, then which section? So there is something called a Crofton formula which actually connects the LKs with the volume, and then you can see that. Okay, so now I'll just go through this very simple exercise that you already saw in Elizabeth's lecture. So this is the Steiner tube formula. I mentioned here Steiner formula because this is how I learned. So what is this formula? You take a nice smooth set A in Rn. Here Rn is R2. Now you might say that I'm saying smooth, but I have taken a triangle. The triangle is not smooth. So point is that you can take any set which has positive reach. Now what exactly is the reach? So anything which around which you can roll a coin of positive radius, that is a set of positive reach. Okay, so you draw a set in R2 and take a coin and roll it around the boundary of the set. If the coin is rolling in such a way that every time the coin touches the boundary of the set exactly at one single point, that means the set has a positive reach. Now the question is, what is the size of the coin? So the size of the coin may matter. Okay, so bigger the size of the coin, difficult it is to check whether it is touching only at one single point. Smaller the coin, it is easier to roll it around. Okay, so if there exists such a coin, then the set has a positive reach. In this particular case of a triangle, which is a convex set, for convex sets, the reach is infinite. So convex sets are very, very nice. So you take any convex set or sets of positive reach, and then you construct a tube around it, which in other ways is some sort of an inflation of the set. Okay, and how do you define that? This is how I have defined it. You take all the points x in Rn such that the distance of x with the set A is smaller than or equal to rho, which is equivalent to looking at the Minkowski sum of the set A with the ball of radius rho. Okay, so you are looking at basically a set A Minkowski sum with this ball of radius rho, and this is the inflated set. Now you look at the Lebesgue volume of this particular set. Turns out it has a very nice Taylor series expansion. It has rather a polynomial expansion, and this polynomial expansion, the coefficients of that have very interesting characteristics, and or rather a lot of interesting features of the set A are hidden in the coefficients of this particular polynomial. As you saw in Elizabeth's lecture, this character WnI, which is basically represent the volume, the appropriate volume of the ball. So this is the ball part, which is basically coming from these corners, and here it is the one-dimensional ball, and here it is zero-dimensional ball. And so this is telling you something about the set A, and this is just telling you the inflation part, how much inflation. Okay, so
Question.
yes.
So if A is a lower dimensional object, your tube will be higher dimensional.
Very good point.
But then the sum is up to the dimension of A.
Yes. So which is why when rho goes to 0, the thing will be 0.
Yeah, rho.
So if you take a disk in R3, okay, you take a disk like a CD and embedded in R3, the tube will be a pizza or a cookie. And then as the dimension, the thickness of the cookie goes to 0, the volume is 0. And that is what is. So very simple, just to warm us up, what exactly are these LKCs? If you take a box of dimension ABC in 3 dimensions, then L0, the Euler-Poincare characteristic, is basically a solid box. So Euler-Poincare characteristic will be 1 because it's one single connected component. L1 is telling you some sort of a one-dimensional measure. And now a one-dimensional measure of a cuboid, we know it is not A plus B plus C. But A plus B plus C is something that you must have already seen when you fly. When you all fly, you must have seen that the dimension of the airlines mentioned that the length plus breadth plus height of your suitcase should be fixed. It is not the entire perimeter, not the volume, not the surface area. It is exactly L1, which is actually given by the. So L2 is something similar to the surface area. It is just a half of the total surface area, which is related to surface area. L3, as we all already agreed, that it is actually the volume. Now, this is for the box case, which is not smooth. Go to the smoothest possible set, that is a ball. And then you can actually, this is just simple, like really just writing down the polynomial of r plus rho to the power of n. And I'm sure all of you know how to expand this using binomial formula, so I'm not going to do that. Okay, when you do the sphere computation, the same thing, just subtract the inner sphere, inner ball. But notice that the sphere has a very interesting characteristic. In case of the ball, all the Lipschitz-Killing curvatures were non-zero. Whereas in case of the sphere, all the alternate Lipschitz-Killing curvatures are actually 0. So again, it is a very strange kind of a behavior that it is giving me some sort of an information about the set which is under consideration. And this is very similar to what we already see in Euler characteristic. For example, a zero-dimensional ball has Euler Poincare characteristic 1. A one-dimensional, ball sphere. Okay, and a one-dimensional sphere has Euler Poincare characteristic 0. Two-dimensional has 2, three-dimensional has 0, four-dimensional has 2, and so on. Okay. In general, for a unit codimensional manifold, every alternate Lipschitz-Killing curvature is actually 0.
So do these have cohomological interpretation? I mean, these LJs?
Yes. So there are. So for example, Euler Poincare characteristics can be written as a
Right. But the other ones,
dimensions.
yeah.
Yeah. So the other Lipschitz-Killing curvatures, no.
Okay.
So follow-up question.
Yes.
Because for the word curvature, is there some kind of differential geometric gadget that would measure this?
Very good question. So the way I define the Lipschitz-Killing curvatures over here is through this tube formula. But this tube formula, if you actually try to write this analytically and actually try to do the Taylor series expansion, you will see there is a lot of differential geometry which comes in. So you're basically taking an object, embedding it in the higher dimensions, and then now the cube is happening in the normal directions. So already normal is coming in, and then there are places where it is turning. So the curvature is also going to come in the sense like if there is a teeny bit surface area here, how much is it going to blow up and give me the region in the tubular region? So that will basically depend upon how much is the curvature and how much is the outside radius. So turns out, so I have an expression I think for the Lipschitz-Killing curvature which involves a different geometric expression. So the tube formula derivation is actually a very nice thing which generalizes LKCs to a much larger class because actually we can define it from smooth manifolds also. Lipschitz-Killing curvatures also satisfy certain kinematic identities which are very actually useful, and these are the two identities that I just pause for some time and discuss. So let us stare at this and see what exactly are these expressions telling us. So we look at the set A, which is a nice set in Rn, and we look at the affine Grassmannian of dimension n minus k in the big dimension Rn.
You want a pointer? There should be somewhere there. Sorry. In case you are looking for.
Yes.
Oh, sorry.
Yeah, but there's none. The usually will stay here, but now it is not there. I can actually I can highlight here.
I think the laser is in this white thing.
No, not the white, it's a black.
That is.
Thank you. Okay, so consider a very nice set, smooth set A, and look at the n minus k dimensional Grassmannian in the ambient dimension Rn. So basically looking at all the collection of n minus k planes in the dimension Rn, in the dimension n, and then compute what exactly is the Euler Poincare characteristic of this intersection, and then average over all possible hyperplanes. And with respect to what? With respect to an appropriate measure. Now, what is this appropriate measure? This measure
Affine Grassmannian or the linear Grassmannian?
is a fine Grassmannian. Yeah, it's not the simple Grassmannian, but the fine. Everything is allowed. And which is why I have the different measure, because it takes into account all the translations also. So this is something which is like a Lebesgue measure, but on the affine Grassmannian. So it has basically all the rotation and translation invariants. Okay, so yeah, that's what I'm mentioning here. That is the motion invariant measure on the affine Grassmannian. So when you're integrating all the n minus k planes and averaging, what you're going to get is the kth Lipschitz-Killing curvature. So now, for the fun of it, let's put k equals to capital N. So what will we get? We'll just have one single plane and different rotations of that, but this is rigid motion invariant, so it has been normalized. So what you'll get is integration of ln is ln. L0 is ln. So it is basically actually just doing the integration. And this, in this particular form, is called Crofton formula. However, if you actually integrate some other Lipschitz-Killing curvatures, that is, instead of integrating the Euler-Poincaré characteristic, you integrate, let us say, the first Lipschitz-Killing curvature. Then what do you get over here? It's actually k plus 1. Okay, so if you change this index also changes, and that is the Hadwiger formula. Okay, so this is just a simplified version, so I'll just mention the Crofton formula. Now, this is quite an interesting result because there is a parallel in baby probability that we all study that is called the Buffon's needle problem. The Buffon's needle problem basically says that you have a ruled surface and then you throw a needle and then it lands on the ruled surface. Then what is the expected number of intersections that the needle has with the ruled surface? So something very similar is happening here also. V is fixed. Okay, in this particular case, V is the ruled surface, and the needle is randomized now. So it is basically integration over all different configurations of the needle. So it's a little different, but very similar. And then here it is depending upon turns out that the result is actually only dependent upon the geometry, which is some sort of a measure of the set A. In the Buffon's needle problem also, the expected value turns out to be just a function of the length of the needle, and does not matter how curved the needle is or how twisted the needle is. So in probability class, many times we also talk about Buffon's noodle problem, not just the needle problem. You can also throw a noodle and the answer does not change. A little generalization of this is something called the kinematic fundamental formula, in which the setup is, I mean, at a very basic level, very similar because there is some sort of an averaging happening when the dynamic setting of something is changing. Here, what is happening is we consider two sets, M1 and M2, smooth. And what I'll do is I'll fix M1, and then I'll look at all possible rigid motions of M2. So M1 is fixed, you change, rotate M2 and see if there is an intersection. Shift M2 and see if there is an intersection, and then rotate. And then measure the Euler-Poincaré characteristic of these intersections, and then average all those Euler-Poincaré characteristics. Turns out this again has a very beautiful expression, and it has this formula which very surprisingly depends only on the Lipschitz-Killing curvatures of the individual manifolds only. There is no curvature term which is appearing. So why am I highlighting this here? Because the Lipschitz-Killing curvatures, they have a lot of invariance built in. So these are global geometric functionals. A lot of information about these global geometric functionals, which is not very much related to the very intricate differential geometric structure, and that is totally gone here. I mean, it's not much seen here, and that's very striking in this particular example. So now I'll talk about the Lipschitz-Killing curvatures of excursion sets of random fields, and so far what I have done is I defined what is generally a random field, and I also tried to tell you what exactly is an excursion set. It's basically points, collection of all those points where the function takes a value higher than a threshold. And so now I've gotten a random set, and now I want to measure certain functionals of these random sets. What are the functionals? They are basically the Lipschitz-Killing curvatures that I'd be interested in. So what I want is there any distributional characterization of these Lipschitz-Killing curvatures of the excursion sets? That is, the Euler-Poincaré characteristic of the excursion set is a random variable. Do I know the distribution? I know it is an integer valued random variable, but do I know the distribution? Do I know at least the mean value? Do I know the variance? Okay, all these kind of questions are very valid questions which we want to answer. So first, I'll just begin with the mean behavior and in a very restrictive setting. And at some level, it's just asking very basic questions itself is quite hard, as some people in the audience would know. That and I'll just quickly go through and then I'll show you what exactly do I mean. So the setting over here is I have a smooth random field, a smooth manifold which is d-dimensional, and I have a n-dimensional random field which is defined on this d-dimensional field, a parameter space. So I have a d-dimensional manifold, and each point I have a n-dimensional vector. Okay, at each point n-dimensional vector. And these n-dimensional random fields are supposed to be smooth Gaussian random fields, and they are IID. So smooth Gaussian random fields basically means that smoothness is what you already know. So it is basically almost sure smoothness we are talking about, or relative smoothness. And Gaussian random field basically means that at every point, the vector that you obtain is not only Gaussian, but if you take a collection of points on the parameter space, the joint distribution is also Gaussian. Okay, so then such a random field will be called a Gaussian random field. And then I consider a smooth deterministic function. Let us say just the sum squared, y1 square plus y2 square plus y1 square. It's a simple function, right? Sum of squares. Then I define a new random field, which is little f. Okay, so now what is this little f? You started with the manifold, defined these hairs on these manifolds. Now look at the norm of these hairs. Okay? And that is this little f. This is the random field. Now define a new Riemannian metric on this smooth manifold, which is induced by the covariance structure of that smooth Gaussian field. Okay, and that is given by like this. Okay, if you have little too much to handle, but basically you have a new metric which is defined on the manifold M, and this metric has the information about the random field which is defined on it. So there is some sort of information, mixing of information between the manifold and the random field.
Can I ask? I'm a little confused. So your field is not a section. I mean, it's just a section of the trivial bundle on M. I mean, can you? Right?
No. So what I'm thinking is basically here I have just, you can think of this as you have a random field which is defined on the entire Rn.
Right.
Okay. And then you restrict your random field to the smooth manifold M. Just restriction of that. Okay. So you can think of this as sections and all, but I don't.
In the sense that I think this is corresponding to the trivial section. You've not assumed any twisting of the.
No. Okay. And also it's very important, actually, good point, that the manifolds that I'm looking at are very simple, orientable surface manifolds. So there is no complex structure which is present in the manifold.
I have a question.
Yes.
So your Y1 is somewhat special as opposed
to other. So YIs are IID in the sense that they are independent and identically distributed. So knowing the distributional character of Y1 is like knowing the distributional character of all those YIs. So which is why I'm just saying Y1. Okay.
New Riemannian metric, can you just say a couple of words?
Very good. So consider the random field M to be the sphere S2. Okay. Define your random field. This instead of n-dimensional, just take unidimensional. Okay, one-dimensional random fields. And what are these random fields? You basically consider the Laplace-Beltrami operator on the sphere and look at the Gaussian linear combination of these eigenfunctions of the Laplace-Beltrami operator. Okay, take the covariance function of this particular random field. Okay, you will obtain certain expression. After a little bit of manipulation, let's say some constants and adjustments, you will see that actually the covariance of this particular random field is actually like an inner product between the points on the sphere. Okay, so these kind of random fields, so they will have this kind of a structure in which the Riemannian metric which is on the sphere is actually just a constant multiple of the original Riemannian metric on the sphere. This is the usual connection. So it is just it is the gradient of the field Y1 in the direction X. So X is a tangent vector in the on the manifold M, and Y is also, sorry, Z is also a tangent vector in the on the manifold M. So you fix a point, look at the tangent space, take two tangent vectors, look at the derivative of gradient of y1 in these two directions. These are real numbers because y1 is a real value random field. Now this is a random variable, this is a random variable. They all mean 0. So it's just product of two random variables. Now you get the expected value of that. It's a real number. Okay. So this is what I will call the new number. Okay. And it's clearly going to be also definite, and all those things are because of the non-degeneracy that I have in the Washington. Any questions?
This difference in the
With whose dimension?
the covariance matrix.
The covariance matrix will be exactly in the same dimension. So the same as the usual n by, so if this is d by d, if this is d-dimensional matrix, this will be a d by d matrix. Now in this particular setting, if I look at the mean value of the Euler Poincaré characteristic, this turns out to be having a very nice expression. Now, let me start from this side. Here, I see that there is this LGM, which is the Lipschitz curvature of the manifold M, but this is not the usual Lipschitz curvature. It is Lipschitz curvature with respect to the new Riemannian metric. Okay, and this is where I think I thought I had a slide, but Sivaguru asked me if there is any differential geometric expression for these Minkowski Lipschitz curvatures. The answer is yes, in the sense that if you take a n-dimensional ambient space, and if you take a d-dimensional, let's consider n-dimensional manifold, and the LK, the k-dimensional Lipschitz curvature is basically the integral over the manifold, a smooth manifold without the boundary. It is an integral over the manifold of the trace of the curvature tensor, which is the 4 form, raised to the power of n minus k divided by 2. Now, this might be a fraction. Clearly, whenever it is a fraction, it is 0. Okay, and whenever it is an integer, you integrate it. Okay. In other words, you can also write it as a integral with respect to the second fundamental form, and that is precisely what Elizabeth was talking about in terms of integrals with respect to symmetric polynomials of principal curvatures. Okay, so this is something which has the information about the manifold plus the geometry of the random field also. But if you take something which is a random field which is isotropic, then what happens is the new Riemannian metric is just constant multiple of the original Riemannian metric. So this actually has exactly the information about the Riemannian manifold. And not only the localized structure, but only the global structure, which is actually just the global geometric functions. And then there is something else which is floating around. I'll come to that a little later.
So when you say isotropic, you meant all the Gaussians are independent?
Not only independent, so if there is a group structure, it is actually preserved. It's like a stationarity on the manifold. Okay. And this is something that I will just hold on to it. But now go back to this side. What exactly is this side doing? It is taking expected value of the Euler Poincaré characteristic of this excursion set. Now, what is this excursion set? Go back to what I had just said. When Puvi asked me, is it some sort of a bundle or a section? I would always think of this as the random field is only defined for the entire Rn. Okay, and for the entire Rn, you fix a threshold, so you know the random set. Now, n is something which I'm throwing into this Rn. So there is intersection. Okay. Now you keep changing your randomization, that is, keep changing your omega. You keep getting different realizations of the random field. Your random set is changing. So in some sense, it is looking very similar to the kinematic fundamental formula over here. Here, M1 was fixed, and this was changing, and changing in a very uniform fashion, Lebesgue measure type. Whereas here, the change the integration is happening with respect to the randomization, which is a Gaussian randomization, which is why we would call this the Gaussian kinematic fundamental formula. And this was basically proven for a simpler version by Robert Adler in 1981, and the generalized version was given by Jonathan Taylor in 2006. So this is looking like a kinematic fundamental formula, but recall in the previous deterministic version of the kinematic fundamental formula, we were averaging Lipschitz-Killing curvatures and we were getting some products of Lipschitz-Killing curvatures. Whereas here it is Lipschitz-Killing curvature plus something else. Now what is this something else? This is what is given here. So it turns out that this extra factor that comes out, which should be some sort of a Lipschitz-Killing curvature in the previous case, is similar to Lipschitz-Killing curvature in the sense that this also is a coefficient in a tube formula, but not in the usual Lebesgue tube formula, but rather in the Gaussian tube formula. So what you do is take the set, inflate it by the ball, but instead of looking at the Lebesgue volume, look at the Gaussian volume. The Lebesgue volume, the Taylor series expansion was finite Taylor series expansion because the degree is fixed. Degree is the dimension of the ambient space. Whereas here, the degree is actually going to be infinite. It's an infinite Taylor series expansion. And the coefficients are called the Gaussian-Minkowski functionals. Why Minkowski, not Lipschitz? Because it's the order which is shifted. There is a very nice integral representation for this particular expression, and which relates to a work by Simeon Olesker, wherein he talks about valuations, and he talks about specifically rotational invariant wave valuations. Rotational invariant valuations are very much similar to these linear combinations of these Gaussian-Minkowski functionals. So that's what I just said, that it is in flavor. It is very much similar to the kinematic fundamental formula, and it's quite remarkable that it's a very neat expression.
So one thing, somehow it's the standard Gaussian that's coming in, even though the underlying Gaussian field is not standard.
I mean zero.
Okay.
So the underlying field also was unit variance and mean zero.
Okay. Okay.
So it is standard Gaussian.
And you had IID components.
Exactly. So now exactly that's the reason that I have this now. So I was working with one researcher from Rome, and he collaborates with people who analyze this cosmic microwave background radiation data set, and they look into these kinematic fundamental formula, particularly expected value of the oil content characteristic, to identify if the universe is isotropic, blah blah. Don't ask me this question, but yeah, something that it is. It is something which is related to that expression. And then what he was so when we were collaborating, he was telling me that it is actually quite interesting to see if there is some sort of a generalization of this particular expression when the components of the yi's are not IID. Because the next generation of CMB data set is supposedly non-identically distributed Gaussian random field. This is our assumption. Okay. So then we started working, but then he got busy and he left the project, and some other people joined him. But then this is the setup. So it's very similar to the previous one: smooth manifold and Gaussian random fields. But now they are independent, but not identically distributed. And the distribution, the joint distribution, is given by some sort of this expression. Okay, so each yk induces a Riemannian metric gk on the manifold end, such that it is just a constant multiple. So what Gautam was asking, can you give me some sort of a feeling of this new Riemannian metric? The new Riemannian metric we assume, because if we are on the sphere, this is CMB type of experiments. Even in the manifold also, we want to work with only those yi's which induce this type of a Riemannian metric. Okay. Then this is the result that we obtain. The expected value of the Euler pointer characteristic of the excursion set turns out to be the same expression, just this new expressions over here now, and this is the usual Lipschitz-Killing curvature, because I already taken into account the constants. And this new expression over here is a bit of a lag. This is now the Gaussian expansion, of course, but with respect to a weighted ball. And this ball, this weight of this ball has the information about the dependent structure between the yi's. Covariance between among the randoms. Okay. And this is something that we had quite expected. It was not very surprising at all. It would have been surprising had we not gotten this result. But what was perplexing was that the computation was quite pretty not looking good. Very ugly computations. Very lot of manipulations. But eventually the expression looks nice at least. So the idea of the proof is very simple. Many people over here already are experts in this. So something which is a generalization of the Katz's formula. What is the Katz's formula? The Katz's formula basically talks about counting certain types of events or critical points. Here I have just mentioned a generalized version of this, and this is exactly the expression that we use. Of course, with lots of conditions. And these conditions, if I write, I think I'll need 4 slides just to write down the conditions. But the good thing is at least the expression exists. But the bad thing is the conditions are so bad that it's very difficult to check. If you give me a generic random field, it's almost very difficult to check the conditions. The conditions involve basically some sort of modulus of continuity bounds, some conditions of the regularity of the maxima of the distribution, and some more conditions which are related to covariance structures. But they are all very easy, not so easy, but relatively easy in the case of Gaussian. So which is why these kind of expressions are very better to work with in the case of Gaussian. And we have some, this is why we kind of could go through this computation. So this is basically counting the some type of critical points. Now, very quickly in the last few minutes, I'll quickly go through some asymptotics. So far what I talked about is just the mean behavior. Mean behavior also not of all the Lipschitz-Killing curvatures, just one Lipschitz-Killing curvature, which is a Euler-Poincaré characteristic. But now you might say that, well, you can reconstruct other Lipschitz-Killing curvatures from the L0, the zero Lipschitz-Killing curvature, using the Crofton formula or the Hadwiger formula. Yes, it is possible, but those Crofton Hadwiger formula, they are very restrictive in the sense that they work only in the case of nice bodies. Okay, so these excursion sets may not be so nice. So if you impose certain conditions on the random field, then the excursion sets are nicer, and therefore you can actually use them. So with some additional conditions, one can actually get mean behavior of the Lipschitz-Killing curvatures of other functionals also, of excursion sets. So what is the setup? The setup is that I have the same random field, which is defined as a manifold, but earlier I didn't mention the generic conditions, the conditions which were basically regularity conditions in the generalized Katz's formula. They are so big that intuitively also it's very difficult for me to explain what exactly do they mean. But here I can actually just highlight a few conditions which are necessary for proving limit theorems for Lipschitz-Killing curvatures. So there are 3 types of conditions which are usually required when you talk about limiting distributions for Lipschitz-Killing curvatures or general geometric functionals. First is Gaiman type of condition. What exactly does it mean? Does it involve? It basically talks about smoothness of the covariance function R of the random field. Okay, and this basically ensures that the geometric functional of interest are square integrable. We are talking about limit theorems. The kind of limit theorems that I'll be talking about are central limit theorems. So the object which is involved has to have some sort of regularity, some sort of integrability condition. So if I have enough regularity, enough smoothness of the random field, the geometric functions which I define from those random fields will have some sort of an integrability condition. And that is a Gaiman type of condition. Second is an Aquinas type of condition, which basically talks about the boundedness of the joint covariance function between the field, the derivative, and its Hessian. So you have covariance between the field, the gradient, and the Hessian. There are 3 types of fields now. You talk about the covariance function between all those combinations. This covariance function should have some sort of a boundedness condition. That is, it should be bounded by some function which itself has to have some sort of a decay. Okay, that is, if 2 points are far enough, the covariance should decay at certain rate. Okay, so that is basically this Arcuris type of condition, and this is very crucial in getting boundedness of the limiting variance. The limiting variance should not go up. The third condition is basically a condition on the spectral density of the covariance function of the random field layer. And that basically is saying that the spectral density at 0 is positive. And this is necessary to ensure that the limiting variance is non-zero. That is, it is a non-degenerate limit that I'm going to get. Now, this is something which is very interesting because it's very difficult to check if what kind of fields. It is a reverse characterization. What kind of fields are there for which this is satisfied? So for us, when we wanted to prove the central limit theorem, it was just very obvious that, okay, let's take this assumption and work through. But then what are the fields for which this actually is working? That is quite an interesting question, and which is why the original question, so this is not the necessary condition, but rather the sufficient condition. So for variance to be positive, the limiting variance to be positive, what exactly is the precise condition? Which is why the lower bounds of variance are very tricky to work with, and that's what many of you are interested. So these are the three types of conditions which we will assume. And then the kind of limit theorems that I'll just be mentioning here are, for example, if you consider just the real line, and you have a random field which is defined on the real line, it's like a process, and you set a threshold, and you look at the points at which the process crosses the threshold. That is basically the boundary of the excursion set. Okay, and you are counting how many times you do this crossing. So this number of crossings of you, the central limit theorem for this was proven by given by Slud and Kratz in a series of papers because different settings. In Slud and I think Kratz 97 and 01, the setting was that the level U was fixed, whereas in 2009 paper the U itself is changing with P. So as the parameter space is increasing, the level is also increasing. So at what rate do these two maintain this increase such that you still get a non-degenerate limit? And dimensions 2. Now, if you have an excursion set, you can talk about the length of the excursion set or the perimeter. And that was basically the central limit theorem was proven by Kratz and Leon in 2001 in the same paper as this here. And then capacity functional for excursion sets was also considered by Murray, Kratz and again. And this is my last slide. So with Murray, what we then moved on to prove was that so in 2 dimensions, Murray Kratz went all the way to dimensions 2, and beyond that, because she was not aware of these Lipschitz curvatures and so on, so like this is a geometric structure that I can talk about: surface area, perimeter, number of components, and we have results. But in higher dimensions, we can talk about Lipschitz curvatures, and then it was a natural question if there is a central limit theorem for that. And then this is what we obtained. So this was basically parallelly, independently done by David Miller and also by us. And the result is this particular result. Herein, you see this the limiting variance. This limiting variance is positive, and it has a very nice expression, but it's very difficult to compute. The cases for k equals to 0, which is the Euler-Poincare characteristic, and k equals to n were proven by Estrada Leon and Viet Hun Pham in 2013 and 2016 respectively. The method of proof is basically now a standard recipe these days. These are basically functionals of a Gaussian random field. So they can always think of this as basically some functional, which is square integrable, and it is a functional of the underlying Gaussian random field. So I can always express this as some sort of a expansion in terms of the Hermite polynomials. Of course, higher order Hermite polynomials because in high dimensions. But that exactly is called the Wiener chaos. Once you have this Wiener chaos expansion, there is a standard recipe that you control these coefficients which are appearing in the Wiener chaos and control and show that the fourth chaos basically is behaving in a certain way. That is precisely the Steinberg method. And this is where I'll stop. And that's it.
Any questions?
The independence is still crucial between the different components.
So independence is still very crucial, and we cannot get rid of that. However, if you have independent structure which is homogeneous in X, that is at any given point it is homogeneous, then it becomes a very strange kind of a field, but that can be done. And we felt that it was very strange kind of a structure because the covariance in it does not depend on X. Very strange.
Okay. And, though you said not to ask further, but is the Gaussian part of the CMB clear? Why?
So it depends on what your religion is. So some religion believes that it is Gaussian, the other religion believes it is not Gaussian.
And this thing there is statistical testing or something that
Statistical test cannot tell you the truth, right? It will, a statistical test will tell you what you believe. Exactly, nice. It will tell you what you believe, or it will tell you how bad is your belief.
Okay.
It will never say that your belief is wrong.
I'm asking for own selfish reasons. So if you change this to not a Gaussian random field, but
very good question.
Something else,
yeah.
Usually it seems very hard to check. And, yes.
Yes. So so that reminds me. So I basically wanted to add a few more slides, and I was thinking that maybe that will be too much, which is why I didn't add. So now that you asked, the question is why Gaussian? Okay, the question of geometric functionals of excursion sets of random fields is a very natural question I can ask in a general setting. Okay, then we have to go back. Okay, where did I use Gaussianity? Where it can truly just fall flat. So the Cartwright's formula is one place where Gaussianity is very easy to work with. But the other distributions will be very difficult to work with. But Cartwright was only to compute actually the precise expected value. Whereas if you want to do a central limit theorem, then I don't need any of these fancy expectations. What I need is some sort of a mixing behavior. If the underlying random field has strong mixing or strong, very fast decay of correlations, then there is a chance that one can actually prove. And this is precisely how it is proven for non-Gaussian random fields by Evgeny Spodarev, Bulinsky and Spodarev, and also Spodarev independently in another paper. So in 2017-19, there's a bunch of papers which talk about central limit theorems for volume and of excursion sets, for mixing random fields, and big fast decay of correlation functions. So different types of mixing basically. And with Yogi and Tulsi, it was in the abstract I had mentioned we'll be talking about joint works with Tulsi and Yogi, but so there we talked about different types of random fields, but a discrete setup. Here I'm talking about manifolds. There it was graphs, and we looked at random fields defined on graphs, and we looked at local functionals, and we proved central limit theorems under very generic conditions of mixing. So some sort of strong alpha mixing or beta type of mixing or correlation decay. So those also work. What you need is basically some sort of a decoupling. When you go far enough, you can actually write this as sum of independence or weakly correlated objects. And that can be done because here this has an additive structure. This can be written as a sum over the kth Lipschitz-Skirring curvature over the big box can be written as a kth Lipschitz-Skirring curvature over small boxes. And that is the additive structure of LK, which was very useful. So if you have an additive functional or a sub-additive functional, you can again invoke these mixing type of arguments and include central limit theorems. Of course, for the limit to be non-degenerate, that's a different ballgame altogether.
Any more questions?
I have a question about the background thing, the Gaussian tube formula. In that there were some coefficients. Can it be proved, like, or is it obvious or something that if I look at only k-dimensional submanifolds of Rn, among those it is maximized by k-dimensional linear subspaces?
I don't know. It's a good question because it also we're talking about maximization of a functional by certain types of sets.
Yes.
So we know that for Gaussian, the half space plays a very significant role. So maybe there is something.
For like k-dimensional, like
I
smaller.
understand. Yes, yes. Yeah, there could be something. I've not looked at it. That's a good question. Thank you.
Okay, any more questions? Well, if not, let's thank Shrika again. Have a coffee break.
Yeah, there will be a conference photo also.
Maybe take it on a selfie with Kaushik. Selfie with Kaushik. So where is your cutout? Cutout is cutout.
Why me?
But that's the standard.
They might your job.
Yeah, you can't hold a day job like cab and also be
But if you should turn off the live stream. The last lecture. Sorry. You can't figure out where somebody is, so it just keeps oscillating. Yes. Between that person and
So the reflection it gets confused. Our this technology is far more advanced than what our department has in the which is okay. Excuse me. This way.
what the cameras. The camera. We Veena took it. She died. Not impossible. Maybe a few. Not taken care of properly.
Because I attended a course. So the point is that there is only one proof that exists of that inequality, which is through linear decomposition. Yes. So it is related to equivalence of these things.
This is interesting because for very selfish reasons. Gaussian function for some very strange reason is never seen anywhere else. Nobody talks about it. Of course, it is not very interesting either. I don't think that it is very interesting. But it is some object which has shown up. What are the properties? Other than that, it is appearing as a coefficient in the Gaussian formula. I don't know anything more than that. Except, of course, I have the integral representation which involves the Hamid polynomials and the Gaussians and so on. But so through that, basically, I was mentioning that is related to simulants. That simulants, basically, every rigid motion element is integral of norm of the body, norm of the x times the inner product between the norm and the normal and the
You integrate over the normal.
correct, exactly, correct. And this is precisely the same integral.
They are going for the picture. I think we should go.
Sure.
Yeah, but I'll find it.
You go. You go and join me later.
I don't know. I usually don't drink a lot. I try. I take some tea. I guess.
Like, you want to find what exactly?
So yeah, so it's take this notion of footing.
You floating body or the convex body? What do you mean? So you approximate So this one gets approximated by polytopes P, like any dimension, so that's a cavity. So this is given, right? So you know, like different metric or whatever. So some metric T, P, and K is small. Is it a determinant?
Might have to write a bit of it. Yeah, let's just fix it one.
And then you want to know you want to take the floating body of this?
Yes,
So you want this is given and you want this and as far as I know, there is like, that is I don't think about
Sure, 100%. Done.
the projector's on.
Yeah.
So mind bending.
It is Piyush Srivastava, and he will continue his talk from this morning.
So just to continue from the morning, so we stopped with this. So we looked at the ball work mainly, and we saw this isoperimetry result starting from the work of with Hasselgate conventional tire piece. So it says that for every we have this convex. And if any partition it into S1, S2, S, so that S1 and S2 are sort of far in this sense that if you take any line segment, then along the line segment, the distance between S1 and S2 is at least 3 times the value of the line segment. Then the volume of whatever is that, at least. So this is of course the natural thing, minimum of the volume of S1 and S2. That's the word here. Times something which is just depending upon. So in particular, T we saw can be taken to be delta by T. Distance between in any norm, we fix a norm, and if distance between S1 and S2 is at least delta, and the diameter of the body is the same norm. Yes. Okay. So that diameter. Okay. So this this is what we want to prove. And we'll give the sketch of the proof. Actually, not with this 2T. That is like everything will be in one dimension, but the 2T will be slightly more complicated in one dimension. We'll do it with a weaker thing, which is just T. Should work out easily. But yeah, that the calculation will not be the point to see how it goes to one dimension. So this will happen via this localization. lowest location lemma. So it says that if you have lowest DNS, which integrate positive numbers in the whole place, then you can find a needle. So what is a needle? A needle is a line segment along with the linear function of the line segment. Linear or a affine function. So it need not be 0 at 0. And then says that on. So if you think of that as a needle, like the function is describing the radius of the disk at each point, then in that measure also the function is integrated to something possible. So this is now a one-dimensional property. So these two inequalities.
Second one is H.
Yeah, H. And it's maybe not intuitively hard to see why this should be helpful here. Suppose this fails. If this fails, then essentially some two of these things will have to be true. So two such inequalities will be true, and then we'll go to one dimension. So let's
If I may say so, I mean, the above one, this is a quantitative statement, while
Yes.
here you have a qualitative statement. So it's
yes, but we'll see. So I'm saying, so if this fails, so let's see. If this fails, I'll write down two such inequalities. Then they'll become two such inequalities that are linear in one dimension, and then we'll again get back to qualitative stuff in one dimension. Yeah. This is the version of it. So suppose this fails. So suppose we find some S and let's assume that we do enough pre-processing so that everything is fine. Like
Piyush, can you write a bit bigger for the camera?
okay, yeah, I'll do that. So sorry, sometimes it's converging to I'll do that. So now so I'll assume all the regularity conditions I want. Like I'll assume, for example, that whenever I want they're closed or open or whatever. So like this, I assume LSC, for example, here. So at least I want open sets. So okay. So those things I will not care about. They can be. There might be errors, but they can be fixed. So now so I have to. So suppose it fails. So suppose. It fails, that means what happens? So what happens? That means there are S1, S2, S3 which satisfy this. So there's a T, and this fails. Okay. So that means that what is happening is that so this I will just write it as alpha T because I will not be doing it with this one. But so I have that volume of S3 minus alpha T volume of S1 or other. So the fact that this has failed is exactly the state that both of these things are true. This has failed means that some S1, S2, S3 exists for which this failed. So these two things. Now we are in this situation. For some G and H. So what is that my G? So G is.
And here when you take it's alpha of t, you think of any function, not alpha times t.
No, alpha of t, yeah, because it won't matter. In the end, I will prove it for some alpha t, which will actually be just t.
Okay.
But you can also do it for two. So this reduction will work for any alpha t. Then the one dimension the actual quantitative thing is more complicated to do for. Okay. I'll maybe even drop this. I'll just give dependence upon t. So just understood. Avoid clutter. So then, like G of just I of S1 alpha minus I of S3. Yeah, so then I want that S1 should be open, S3 should be closed, something like that. So then this is exactly the hypothesis of this. So we go and we find some needle and this right. So some AB and so that this is happening. So what is this? So this AB.
Sorry.
Oh, yeah. So let me just write the first one, second one is just changing 1 and 2. So this is going to be so this. And the same thing for 2 also. 1 replacement. So we have these. But now let's just think about what are these. What is going on here? So now I can just I can just think of what S1, S2, and S3 are doing on this line. So on this line also there is S1, S2, S3. So now let me just instead of introducing a new notation, let me just think of these as integrals on the line. Right? So this is really bad abuse of notation, but this is just not right, but we know what it is. So then drop this. So yeah, and this is where I was in a log concave. Like we are already at this level of log concave function, so we could have started with a more general thing here also. This is a log concave function, LT, because it's a linear function, so it's concave. Its log is also concave. So this is a nice log concave function here, and basically what we have is so there's some. So let me just erase one more time and just say that. So let me just use.
You assume that L is positive. Or, L is positive. You assume that, right?
Oh yeah. Oh, I didn't write it here. L is linear and it has to be positive. Yeah, I'm always thinking of it as a radius. We always think of this as needle as a frustum proponent. That's the. So GT where GT. So we now forget everything about this. G is log concave. And G is log concave on a line. So it's also unimodal. So it's picture G. Since it's a log concave or concave, it has to be something like this. So this graph. So and then to prove this with equal to T.
No, what is unimodular?
Oh, unimodal. It has
unimodal.
Oh, unimodal. Yeah. So it's just yeah. So if it becomes maximum somewhere, like
Okay.
you cannot
Sure.
cannot have a local maximum. Yeah. So it can't have maximum, then something lower, and then again maximum. That's all it is. So yeah. So at this point, so let's just see what is going on. So it's intuitively it seems that the worst case would be when this or the interesting case should be that there's S1, then there's S3, and then there's S2 on the line, like in this way. And if we can prove that there this cannot happen, then we should be done. I mean, then it should not happen also in the general case. And so this will fail, and therefore this will fail, and so we will have our inequality. So let's just see that that is the case. Okay. So let's look at the intuitive result. So this holds for. So let me just write it now. So. So let's just see. So but what does so this is what we have. So let us consider a special case. But also intuitively. Intuitively the worst. Is where there is one. Like from here to one on this line. Of course, in general they could be interleaved, but if we can do this, we can do that also. But let's just do the calculation for this. So we want to show that this kind of a thing cannot happen, and it will just be fine. So what's the reason? So yeah, so we have this picture. So it's a log concave function. Or I don't even need log concave. And I am drawing some numbers. Right? So this is 0. This is 1. I know that this distance is at least. Oh, I'm sorry.
Maybe yes, yeah.
Yeah. So let's go ahead. Yeah. You know that this distance is at least because S1 and S2 are. So this part is S1. This part is S3. So this is greater than T. So all I'm going to say is that the mean of this guy, if I take the integral and divide by T, that is at least the minimum of these two, which is again because it's sort of clear because so whatever like basically take the minimum of these things and on the other side it's always going to be below that, so the mean is going to be below that one. So if you take the smaller of the two, that is going to be less than the mean in this interval. And this of course I put the
Requires a max
not necessarily, but I said will work even if it is not.
Okay.
So even if the picture look like it's still true because the minimum now is on this side. Okay. So the mean in the middle guy is always going to be more than the mean on the other. So we get basically that the integral of G ds 1 over T. So whatever the 1 over the length of this, which is at least T. So I just maybe choose the length T. So okay, so the T is which is certainly bigger than this thing, and so this is going to be bigger than the minimum of the means on the other side. But the means are just the integrals divided by some numbers that are less than 1. So those are anyway bigger than the actual integrals. And that quantity. So that at least proves it for this case. So the proof is it's like double negation. Yeah. So if the inequality failed, then this would have to be true. this cannot be true, at least in this special case, because just G is log concave and so that's where the convexity was. The only place convexity was this is actually there. Right? So this is not, there's nothing here about convexity. Localization lemma is a generic statement. This translation is generic. Only at this one in the one-dimensional analysis that we're using convexity. I mean, also like it's showing that this would be the worst case. So that's also very. So now to argue this is actually the worst case. Yeah. So this. Yeah. So that. So basically, the argument goes something like this, and that. So in the worst case, what can happen? So there is this S1, then there will be some. So it cannot happen that S1 and S2. So there's some S1 part, and suddenly there's an S2 part. So if you start like sort of, of course, it doesn't make sense, but like you start coloring points, and you have S1, 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 S1. Suddenly it cannot change to S2. It has to change to S3 first, and then maybe some S2. Then again there might be S3 in between and S1. So if you draw these things, there'll be some S3 holes in between, and otherwise there'll be S1, S2. And any two S1 and S2 will be separated by at least a distance t. Now, any S3 hole that is of length less than t, just delete it. It has to be, so if it is of length less than t, both sides must be of the same kind, either S1 or S2. So just delete it, add it to whatever it is. That can only hurt us. So you do this. So at the end, you are left with all the S3s are of length at least t. So there are only finitely many such intervals. For each such interval, you can apply this guy. And basically, then it's just a commutal checking that all of one of S1 or S3 gets covered when you do the argument on all of them and add them with the right multiplicity. So that's so the only thing to do is the fact that the distance, because the distance is t, all the S3s that are below t can just be gotten rid of, which just makes things simpler. Now all the whatever is left is like intervals of S3 of length. They're only finitely length. So apply that argument to each of those intervals. You don't care that this one is S1 and this one is S2. Just that this is S3. Here there might be something. And then you basically, if you cover whatever, so the smaller parts, and then when you add all of these up, and you just say that one of S1 or S2 is completely covered by this. And that's the first. So I won't do the details. There's just comment. The only calculation needed is this. So to get 2t, you basically have to do a more convoluted version of this. So it's not just sufficient to just take the fact that it is unimodal. You have to use the fact that it is log concave. Operate approximations. Second derivative. Yes, it's a so in the lower version also it's like one page of serious calculus, but it's one-dimensional calculus, and that's how you get to this. But it's all in one dimension. The rest of the reduction remains the same. The final reduction to that this is the worst case also remains the same.
So it makes a big difference whether there's a 2 or not.
No, it's just to say that this 2 is exact. I mean, it's right.
Okay.
Yeah.
So what is the equality case in this? I mean, what is the type for?
Yeah. So this for this in the worst case, one example is it's the lowest human with give is a tall and thin cylinder. So if you take a very tall and thin cylinder, the diameter is essentially the height, and you just take S1 and S2. So just cut it in half by a plane parallel to the base, and so the surface area is basically, so the volume of S3 is basically just surface area times whatever the thickness is, and that is going to be exactly this. So if you take now E to be delta by T, so because the volume is like the diameter divided by 2 times the surface area of the any one of S1 or S2, and S3 the volume is just the surface area. So you get this factor of 2 by D, which is 1. So this is until 5. Sorry, it's the
445.
4%. Okay. So so this is one I didn't prove the localization. So this takes some work. The basic idea is bisection. You want to say that okay, if this is true, then you first put everything in a compact set. It's true in a compact set. You bisect it. It's true in the compact set of half the volume. You again bisect. This will get it down, but the problem is that if you just do it like this, you might just get to n-1 dimensional space. I mean, like, the limit might be some n-1 dimensional thing, not a one dimensional. So it has to be done carefully. So it is one of the most technically involved parts of the course. But yeah, the final statement is very clear. Okay, so this is for the ball walk, and okay, so now let me just say a few words about how how I can go from this to. So we saw that the ball walk does not have conductance, but something like conductance one can get out of this for the ball walk. So let me just mention that. So this also is an argument of. So this particular thing it appears in. I'm pretty sure it also appears in earlier papers, but also appears in some analysis of some other chain. And it's basically this idea that one way to relate these kind of isoperimeter inequality to conductance, especially for ball walk. So what does ball walk do? It has you have a point and you draw a ball of fixed radius, and if the point happens, and you draw a random point from the ball, if the point happens to be inside K, you move to that. So so what to say that basically what you to relate the isoperimeter to conductance of this, what you want to say is that if two points are close geometrically, like if the distances are so if x and y are close by points, so they have a transition kernel, right? So x has a transition kernel, y has a transition kernel, and they might intersect a little bit. So you want to say that their intersection is also large. So total variation distance between the next step starting at x and y, if x and y are close, should be also close. And this of course will be false for ball walk if you again take points very close to the boundary and so on. So you say, let's say this only holds if you neglect some part of the body, some small fraction of the body. And under these conditions, you can get some version of conductance. So let me just write that. This idea of geometric distance implied is being small, implying probabilistic distance being small is sort of interesting. It has been used for other chains also. This argument is the way I am presenting it from another paper of Roach for a different chain, which I'll mention later. So the property I was describing is something called epsilon. So I'll just give it this name, epsilon delta nu overlap. So this is the name, a bit of a mouthful. But so K is the convex body, and and P is the Markov chain. So P has this epsilon delta nu overlap with K prime. If following a two, one is so K prime is convex. If one the volume of K prime is at least 1 minus epsilon times volume of K for every y in this smaller body. So this is exactly saying that I'm allowed to remove some part of the body, which is troublesome for me. And after I remove that, then this geometric distance, certain geometric distance being small should imply property. That's just a property. We want to say that. So I want to. Yeah, my claim is that if you have this, then this isoperimetry implies some kind of conductance called S conductance. So like a weaker form of conductance that so this is one definition. Second definition. The S conductance of the chain. So this I will write it as there's a S here now, and P is the chain. So P, of course, is always being understood. So this will be so small s is the so this is the ergodic flow from out of T divided by the mass of T. Oh, sorry, this is not right. So maybe that's better. So the original conductance would have been something like this. And here I would have the ergodic flow from this is what the original thing would have been, except this S would have been 0. Here for this that's called the epsilon, the S conductance. And the reason this is good enough is so again this is the watch and signal orbits. Says that so if I so suppose that if my original distribution is diffused with respect to them, so its density is bounded above with respect to the stationary, then so this I am writing in the context of ball walk, otherwise some extra factors are needed here. So this term is similar to what we had for conductance. There's exponential decay, but there is also now this thing which will say that you cannot actually go below ms. So S will have to be small. So if you want to get to epsilon total variation distance, you will have to prove something about something like the epsilon by 2m conductance. Then this term will be epsilon by 2, and then take enough steps to make this also less. The S conductance also can be used to prove mixing, but of a weaker kind. So this is called a warm start. So this is M. So smaller is good. So smaller the M, the better it is. So let's just see how one could. So I'll sketch how one can get S conductance. So now if I want to get S conductance, I have to do two things. What I will show that will show first that any kind of epsilon delta overlap implies some kind of S conductance in terms of epsilon delta nu and this thing. And then the question just becomes, does your walk have this overlap property? And then it's a calculation for the ball walk that the balls are small, it does. So I think maybe let's look at that thing first, that the ball actually has epsilon delta nu overlap for some reasonable. Yeah, so I'm not optimizing anything. So it's many of these things can probably be improved in terms of parameters by a lot of parameters, and like probably are like read closely in the papers you can find the. So, but let me just say that so assume so the claim that ball walk, or maybe I can just use. So ball walk. So on. So I'm leaving some blank space because I'll fill them up overlap. So I have not even defined the ball walk fully because I have not defined the radius that you have picked. So I'll do that also. So let's assume, so just for simplicity, assume that. So this inner ball is actually of radius 1. That's just simplifying. And I'll put. So I'll put the radius. So this I'll say here the R ball, so the ball of radius R, and that R I will set epsilon by n. And delta will be epsilon by n. So epsilon is some free parameter. Delta is epsilon by n. Epsilon. So here is one piece of convex geometry. This is very simple, but I just assume it. So this notation will conflict with previous talk, especially the floating body talk. But so I define Kr to be the set of all points in the body which are of distance at least r from the exterior. Okay. So. I can also just put the boundary. Yeah, it doesn't matter whether I make it open or close. So this is convex. The distance function is concave, and this is convex. This is easy to see. The piece I would need is because of this assumption, the fact that it contains the unit ball implies that this Kr contains 1 minus epsilon. One minus r. This is easy to prove. It's just a direct application of the separating hyperplane. They are all just similar triangles. So all I'm saying is that these points, if you just shrink the body by a factor of 1 minus r, all the points you get are distance at least r from the boundary, and that has to do with the fact that the one unit ball was contained. So. Okay, so that means that at least first condition I get for free, right? So volume of. So this is the first condition of the overlap. And it's also because it's Kr, like for any points x and y, the whole ball is contained in the body. So there is no this fact of this rejection is not happening for me. So now this becomes a geometric thing. So there is this ball around x. And there's this y, which is actually pretty close. It's like, notice the delta, the distance between x and y. So assume, So if X and Y are in KR, so this would be my closed line. If X and Y are inside, the balls are anyway sitting inside K, because the definition of KR. And if this X and Y are very close, extremely close, they're like root n, 1 over root n the radius of the ball. And so so I want to just say that the intersection. So now, I want to say something about total variation distance, right? So one way to upper bound total variation distance is to exhibit a coupling in which X and Y agree. And what's the coupling? This is natural coupling. So you just sample from one of the balls first. If you land in the middle, in the intersection, then you just say that this is the point for both of them. So they become equal. If you land here, then of course this guy will choose this point and the other guy will just choose a reflection along this. So that's a valid coupling. And in that coupling, the probability that they become equal is exactly whatever fraction of the ball is in this, what Fernando and Simonovich and others call a moon. This is the moon and this is the co-moon. So the volume of this, so the my nu. So what is the total variation distance? It's the minimum over all couplings of the probability of X not equal to 1, right? Over X and Y. So this I am showing, I'm giving you a coupling where the probability of X equal to Y is at least this much. So that's what my nu will be. So I want to just, to get my nu, I just want to say that this probability of like this fraction, this co-moon as a fraction of the ball is large. And that is intuitively true. The point is that almost all of the ball is contained within a 1 over root n height of the, like any equatorial plane. That's not quite, I mean, that is true, but that's not quite our situation because some parts are excluded. But this can be like argued, and so this is very precisely done in a later paper of Bangalore and Simonovich. So this calculation can be done. So this, let's call this C. So this is not the KLS paper, but the KLS experiment, but it's another KLS paper. And where this volume of as a fraction of the volume of the ball. Of course, this does not depend upon the radius, this fraction is bigger than, in fact, 1 over e minus 1 or something. So it's like some constant. Whatever that absolute constant is, that is my nu. So we get that.
Depends on delta, no?
No, because yeah. So all I am using is that the delta is 1 over root n, the radius.
Okay. Okay.
That is important. I mean, 1 over root n is sort of important because like all of the mass is there. So
it's a concentration of measure.
Yes, that's the intuition. And I mean, the only thing is that the concentration of measure is for the whole, like the usual thing is for the whole slide, some of that is missing. You just have to say that's not allowed. So yeah, so the intuition is clear, the precise calculation you can find. Okay, so yeah, so this satisfies this kind of overlap.
Did you use this thing for the isoperimetry?
Not yet. I only proved that there is overlap. So that's all. It separates the concerns. So now I'll forget about the ball one. I will just use the fact that there is epsilon delta and u overlap. And using that, I will now go to so from using that and isoperimetry, I will go to S conductance. That's the
choice of nu. What was nu? I mean, yeah.
So nu is this whatever this is 1 over e or whatever.
It's a fixed number.
Fixed constant. Yeah. Okay. This ratio of the at least that much. I think it's exactly that much. I think that's all. Okay. So now we have got. So now we are justified in trying to show that epsilon delta nu overlap implies this S conductance, using the isoperimetry.
Slightly confused. For delta, for that volume to be bigger than constant, the delta has to be same as 2 over n, right? But you have taken much smaller, right?
No.
Delta is the difference between x and y.
Yes.
So even if it is proportional to the radius, you will get a fixed constant. Oh.
No, it will be very far away. So so the concentration of delta it has to be about 1 over 10. Okay, so now you want to say that delta implies S conduction. Actually, that S will turn out to be epsilon. So and how large will depend upon the value. That's what we want to do. This is the part here. Okay, so yeah, so this just requires a little bit of juggling around things. So the works. Make sure it was. So what do I want to show? So what we will show is something like this. That so in fact, what we will show is that this ergodic flow, this kind of a thing.
Again, right?
Large ball. Sorry, even I can't read.
Oh, I see.
It's large. It's written in tiny.
For some S, that S will actually be epsilon. So right now, what we will show? So we will show that the
conductance is large for some S.
Yes. So that's why I forgot. S will be epsilon. So we will show that this ergodic flow of S1 and K minus S1, these two sets we could consider. Ergodic flow from or yes. So let's assume that this one is the smaller. Well, forget is at least the following. So the mu 4 times T means this is the diameter of the body. Diameter of the body, and times the minimum. So this shows that the S conductance is at least what is written. So this is what we
K minus, I mean, you're assuming K minus S1 is S2, right?
Yes, yeah,
Okay.
yeah. I don't know why I wrote. Yeah, I will just say notation. So this is what we want. So I'll not do the full proof. I'll just show how where the isoperimetric inequality enters. And the proof itself is also not complicated. Just that some accounting, some bookkeeping needed, and so basically there will be several situations where it just follows, and then there will be some hard case that is left, and at that in that one you'll have to use isochronometry. So I'll just get.
Very powerful.
Yeah.
Yeah. It's been caught on camera also.
Yeah. like there'll be police waiting.
Destruction of public property.
Yeah, exactly. I have to look carefully at my salary slip next time. Okay, yeah. So we let's just define something. So the point is we have this body K prime, right? This inner body. So it has to enter. So let's just this is this K prime. This is T1 here. Okay, so this is S1, and whatever is here is T1. That's the picture. And similarly, okay. And the crucial thing is defining the following set. So what is called an SY prime, and so that is S1 prime is all those X in T1. They are in K prime S, such that the probability of going from X to S2, not the prime version, but actually the full set, is less than mu by 2. Similarly, there will be S2 prime. It will be, although there is T2, there is probability of going. And the crucial thing is that because of this epsilon delta nu overlap, so X, so it means that so if X in Y and the point is that because there is epsilon delta nu overlap, right? X and so if they were less than equal to delta, then the epsilon delta nu overlap will tell us that the probability of X, so the probability of X dot and probability of Y dot, they are within the total variation distance is at most 1 minus nu1. But the fact that this one going from S2 is less than nu by 2, and here it's going from S1 is less than nu by 2, will tell you that the total variation is actually has to be at least 1 minus 2. That's a contradiction. So this is right. So these are the far sets that we have. Okay, and so now it turns out that so we also now assume these sets are sort of large in the sense that greater than at least 1. So both of them carry at least half the volume of TI. Why? If they don't, if any one of them has less than half the volume, then that means that there is a large so suppose S1 prime is less than half the volume, then at least half of them have a significant probability of going into S2. And that would mean that the conductance has to be large. So that's a simple calculation. There's no isoperimetry needed, it's just arithmetic. So the bad case is when these bad points, which are not going out, carry most of the measure. So this is what we have. And now let's just do this. So So you have to assume a little bit. You will have to assume that D is at least delta, but that is free assumption. If it's not, then just increase the value of D. That's also a valid diameter. Okay, so this is fine. So now, so what do we do otherwise? So okay, so now they do carry most of it. So let's just look at. So now let's try to write down this ergodic flow in this case and see what it means. So the first thing to note is that ergodic flow. So I'll stop writing this thing. So the ergodic flow from S1 to S2, which is what we want to say is large, is bigger than the ergodic flow from S1 to T2, and also the ergodic flow from S2 to T1. Why? Because it's also it's a reversible chain, so that with this, and T2 is anyway a subset of S2, so whatever the ergodic flow is, and similarly, so these are the things we do. Okay? And this is also equal to the ergodic flow from T2 to S1. And these. So let's look at this one, and the same thing will happen for this. So what about this T1 to S2? So whatever so T1 has this bad part S1 prime, which has less than nu by 2. But anything outside that has at least a probability nu by 2 of going, right? Going to the to S2. So this is at least nu by 2 the pi of T1 minus S1 prime. And similarly, this one is bigger than nu by 2. So this pi of S1, S2 is both bigger than this and also this. So it's bigger than the average also. So nu by 4, the sum of T2 minus S2 and T1 minus, but these are disjoint sets. T1 and T2 is a partition, S1 is a subset, so these are disjoint sets. So this is just pi of T1 union minus S1 union. But T1 union T2 is a partition of K prime. So this is just K prime. And now what should we do? So we want to say that this is large. We have to say that it's at least as large as the volume of K prime minus S1 prime union S2 prime.
Now you can bring the iso.
Yeah, now we can bring the isoperimetric. Why? Because we have showed already that S1 and S2 prime are formed. They're at least delta away from each other. S1 prime and S2 prime. So the isoperimetric can be applied to K prime.
I mean, K prime minus this is this your S3 prime.
This is my S3 prime, yeah. So but there's a pi sitting here. That thing was about volume, but that's okay. Everything is divided by the same thing. Okay. So that is fine. So this is.
And because it's overlap, so the volume of this versus volume of K is.
Yeah, then later on we will have to add a minus. So that's where the minus thing will come. So this by isoperimetry will so we get that whole factor. So this T I said, right, it can be chosen to be delta by T. So this becomes This becomes a 2, this is a delta, and there's a t minus delta. Somewhere I might have missed a factor of 2, but yeah, this is the point. Times what? Times the minimum of phi of S1 prime by. But S1 prime was just whatever, S1 intersection with K prime. K prime has at least 1 minus epsilon the volume of K. So this mass, this is at least pi of S1 minus epsilon. And that's what we want. Okay. And yeah, so and all the remaining case where that inequality phase is actually much simpler. There's no isothermal, it's just arithmetic. You get something actually better. So yes, so isoperimetry was needed, and it makes sense that isoperimetry is needed only when this things are sitting close to the surface. That's or the other way around. Things are not sitting close to the surface. Like if everything is close to the surface, you will move. The ball walk will. If it is far from the surface, that's when you need to apply. Right. So this and okay. So now so if you apply all this, you will get the polynomial type mixing. So if you have any fixed epsilon in your mind, you choose the epsilon by n ball walk. You get you put all these delta and t here. So in the end, what you get will be, and then you apply that. The LS this thing. So you'll have to choose your original so if you want to get epsilon not close to pi, you have to choose this epsilon to be something like epsilon by 2m, and then the time that the number of steps you have to make will be some polynomial in n 1 over epsilon and m. M will also show up as a. So that's why it's a warm start. It will not depend upon log m. It will depend actually upon m. And a warm start is sort of not easy to achieve, but in the sense that it cannot just be gotten by random sampling. You have to do some algorithmic thing. So one question is if you can get rid of the warm one. So maybe I will just write down. So this so from this I will not write the polynomial degrees. These are anyway not optimized. Poly in n 1 over epsilon and 1 over m. Sorry, not m. Mixing time. Epsilon close. Stationary. So that's what you will get out of this. It's easy to see to a polynomial that decreases. Okay. So for m warm start, m is the warmth of the start. So if you think about it, so the only thing I assumed about the body is this aspect ratio. The simplest way to try to get a warm start is to sample from the inner wall. That is in the body, but that is the m is exponentially large. Can be exponentially large in principle. So because all you know is that the density, the body could be the whole capital R ball. The density is like 1 over R to the power n, and this one is something like 1 over small r. So the ratio is capital R by R to the n. So it can be exponentially large. So of course this can be fixed by all these ellipsoid like preprocessing. But suppose we now don't want that. We want our random walk to be able to handle these cold starts. So the cold start is that m can be exponentially large. Worst case, it could not even have a density; it could be a single point. So we want to get to this cold start. So the ball walk will not over because the conductance we know is so there are chains which we know can do this. So one example, I'm not sure if this was the first one for which this was proven, but certainly one of the first ones. It's called hit and run. So I don't know who came up with the name. The first published paper with the name is by Lowash, but I'm not sure if. I mean, the idea is old. The chain itself has been described in papers in the 80s, and not even in the setting of convex bodies, just arbitrary bodies, and for good reason because it's a simple thing. So it says you're at a point in the body, you pick a random direction, draw the chord, pick a uniformly random point on the chord, and move to that point. So that's the hit and run. So you just run to some path. So this is nice because this cone example I was giving, this thing can potentially escape that very quickly. It just has to it can move away. I mean, of course, in fact, if it gets lucky, it will completely escape the corner in one step. Maybe it doesn't get lucky. So Lowash in a paper in the late 90s showed that from a warm start, this has good mixing time. In fact, it was not known whether it does better than so this is all intuition. Rigorously, it was not known whether it does better than ball walk for a long time. Although in practice, people have been talking about it. So Smith has a paper in the 70s that is where it looks at this and another variant called coordinated run. So coordinated run is that you don't choose a direction at random, like uniformly at random from the sphere, but from just the coordinate direction. Now this looks very I would say non-mathematical, right? I mean, why should the basis be important? But it is actually quite important because you have like polytopes. Polytopes usually have especially if they're coming in some applications. So one kind of application is you're trying to sample probability density. So like you have some kind of Bayesian inference type thing where you get some set of probability densities which are described by some linear constraint. That's a polytope. And you want to sample one uniformly. The coordinates, like the actual directions, do sort of matter. The polytopes might have sparse representation in that coordinate. So then checking or like finding the length of the chord becomes easy. So this coordinated run also makes sense. That was in fact, so this paper of Smith from the 80s actually mentions both hit and run and coordinated run. And they show that in experiments, it seems to both of these seem to do better than other methods. But the first analysis was with ball walk. Hit and run was analyzed by Lowash with a warm start, using a very nice idea. So this isoperimetric inequality here, which was for Euclidean distance, he replaced it by a new isoperimetric inequality for the essentially the Hilbert metric, but actually not the Hilbert metric, but the cross ratio. So Hilbert metric is like 1 plus the cross ratio. I'll not write it down. And he said basically that if you have exactly the same K R N S1 S2 and it's the same partition, he says that the volume of S3 is going to, and then what is the volume of S3 is going to be at least the volume of S1 times the volume of S2 times the cross ratio, the minimum cross ratio between S1 and S2. So that's a nice paper, and then based on that and since it's overlap kind of thing, so again he has to prove this this analog of the overlap thing that we did. So in fact this idea is here from that paper applied to the ball, and so he showed it from warm start everything works. A later paper of Lowash and Vepala about 7 years later showed that the hit and run walk also mixes from a cold start. From like the dependence upon m is log m, not m. So it can mix from cold start, and in fact, therefore, it can from any point which is somewhat inside the body. Because any reasonable chain, if you start even from a point, you take a few steps, it becomes the density becomes at most inverse exponential. So at most exponential. It's not hard. Like for ball walk, it's very easy. So and their thing was to take the Lowash isoperimetry, which was for this 2t 1 minus t. Which was with this cross ratio, and get a more refined version of it, not with just the cross ratio, but like actually looking at the directions. So that's a paper I do not fully understand. Like I mean, it's a very nice kind of isoperimetry, but it's a different. There's no distance somehow in the view. It's like It looks like an isoperimetric inequality, but here there is a distance.
You mean that constant there is
Yeah,
not coming from any notion of distance that you
Yeah,
can
it is some. Yeah, it can be called, but yeah, it's like some. It's it's itself a functional. Like you take some lines and do some optimization. So here also it's like that, but it's a simple enough thing, and there it. So.
I mean, because cross ratios can also be got as some sort of extrema functionals, I think.
Yeah. Okay, yeah. So that's.
So maybe it's okay.
Yeah, but that one. Yeah. So it is it builds upon the original cross ratio inequality. Cross ratio inequality, the calculations boil down to at least. Yeah, they're non-trivial, but in the end, the non-trivial thing is Menelau's theorem or Seva's theorem, whichever way you look at it. I mean, that's kind of going on. But there it seems to do more. And so that's hit and run. I wanted to talk about. I didn't write what hit and run is, but I think that's. So this coordinate run was not. The mixing down of that was somehow still open, even though like in practice apparently people use it, like there are toolboxes that you can download that biologists use where CHR is called CHR. So CHR is a thing you can just run, like it's a function call. You'll do a random walk on your corridor and there are random points. So but the mixing time was somehow not understood. It's still not understood, but at least now we have polynomial time mixing results. So again, the story is similar. So there's first a warm start mixing time result. There were two papers. One was by Hariharan and myself, and another by Atita and Santosh Kampala, using different methods. So our method was sort of along these lines. So again, we had this overlap thing. We could prove the overlap for some other chain, not the coordinate for some other chain, and then compare that chain to the coordinate. Their thing was more direct. It was like proving some kind of an L0 isoperimetry. So which is like you have like you say that so the L0 distance between 2 points is how many coordinates they differ upon, and so they proved that, but again they had to sort of remove part of the body, then do the argument. So everything was about form stuff. So in work last year, Hariharan and Amit Rajaraman was at that point on the IIT Bombay and myself. So we got a cold start mixing time result. It's not the optimal running time. It's like n to the 9 in the dimension with log and log, but it still depends as logarithmically in the warmth. And recently that n to the 9 was improved to n to the 8, like just last month, basically because so our proof was for the following kind. We defined a new Markov chain, which is what I'm going to talk about, which does not on the front of it, face of it look like coordinate. Proved a mixing time result for it. Then we compared coordinate to it, and we could actually use the other paper, the Datta-Vempala proof of the bomb star, and show that it can now be improved using this new Markov chain to the full bomb star. And so their thing uses this L0 isoperimetry, where they had some isoperimetry that was recently by so I forget the name of the author, but yeah, it's a paper on the archive just last month. So that n to the 9 can now become n to the 8. But that's also probably not the right answer, because there's a lot of this whole thing is going by this translation to this extra other chain. And that other chain is what I'm now going to describe in whatever 2 minutes that I have. So that chain, and it might maybe like experts might remind people of the source ratio. So that, even for that chain, we don't think we have the optimal conductance bound, but not necessarily the optimal mixing time bound, because as I said, conductance is a sufficient condition, but there is a square gap. Like the conductance is psi, and the mixing time is at least 1 over psi, and at most 1 over psi squared, something like that. So there can be a gap of a square. So here's the chain. The chain is the following. So you have body K, and we don't want to throw out any parts of the body. And it looks like in these kind of metrics you have to do that. And part of the thing about the Hilbert metric or the cross ratio is that it somehow distances are magnified near the boundary, and so somehow it's not throwing things. So here also we'll do it, but in a more sort of ad hoc or by hand kind of method. So the obvious thing, and this actually was already there in the Datta-Vempala, is to put some grid on the body. and like then there are these cubes, and you try to analyze the cube. But again, the cubes of a fixed side length, you will be like the cubes near the body don't look like cubes at all. They are like some weird curved things, and you'll have to analyze them. And so what they did was throw away those parts inside the body, everything like a cube, you can analyze. So, but there's a natural thing at this point that you can try, which is to not have just one kind of cube, but progressively smaller cubes as you come closer and closer to the boundary. So this is what we call this multi-scale walk. So this is actually just a Whitney decomposition of the body. So what you do is that as soon as the cube gets too close, so for example, not even this cube, as soon as you come to this cube, which is too close to the boundary, you start bisecting it. And certainly this also gets bisected. Maybe even this one gets bisected. So basically what you ensure is that the following properties. So these are all partitioned into dyadic cubes. So by dyadic cubes, I mean that the vertices are just dyadic rations. So some integer divided by some power. So partition came dyadic cubes with the following properties. One is that if cubes A and B cover, which means that they actually share some sort of part of the surface, then their side lengths cannot be too far apart. Then either they are the same side length or they are just one level below or above. So that's one thing. And the second, which is more important, is that the side length is sort of proportional to the distance to the boundary. And these two are actually related. So the thing is, where am I measuring the side length? Doesn't matter. There's any norm. Okay, but, so yeah, so these are all in the same norm. I mean, so here of course it doesn't matter, but here maybe it can be something. LP is yeah, I think we are side length. So there's constant, really small constants, like less than 10. I don't know that number, but the crucial thing is this. So these two are actually related. I mean, you have to get one, you have to get the other, so they're interplaying with each other. But these are standard constructions, this is the Whitney decomposition construction. And now, and you can do it for any LP now, 1 to infinity, any one of them works. And now the random walk is pretty easy. Like now the whole body has been divided discountably infinite time. You're in a cube. You just assume that you're in the uniform distribution of the cube. You want to go to a neighboring cube. So you pick a point on the surface of the current cube, uniformly at random. With probability 1, there's a unique cube that is operating on the other side. And you basically do the correct metropolis filter on this. So you move to that cube with the correct metropolis filter to ensure that the stationary distribution on the cubes is proportional to the volumes of the cubes. So that is what you would want if you want the final distribution to be uniform on the body. So that's the that's the Markov chain. And the chain is metropolis. I'll not define what the metropolis is. It's a standard trick. I mean, all I want to do is have the distribution on cubes where it's proportional to the volume. And what I'm going to do is to at each time try to move to an adjacent cube by just choosing a point uniformly at random on the surface and then checking if I can move to that and doing it to the right probability. That can be written down. Adjacent cubes. The pi of any cube should be proportional to the volume. It should be equal to the volume of the cube divided by the volume of the volume. And it's easy to see that if you can sample from this, then you can also sample from the body. I mean, just as soon as you have a cube, you just take the information from the cube, sample up, and everything is fine. So you have to mix in this one. You have to get mixing time for this chain. And for this one, yeah, okay, I'm already making many enemies, so I'll stop after this. I will not write down the ad hoc localization, just the.
It's only 2 minutes of enemies. So.
2 minutes. It turns out that for this one, we need an isoperimetric inequality. So I will not write down the inequality, but I'll write down the distance with respect to which we get the inequality. And the distance is the following. So it's sort of like a Finsler-like thing. So we need a. So this can be defined for any LP, but let me just do it for L infinity. Yeah, so for the following. So what is this D infinity? So let me just write it in a. So it's the metric in which the length of any curve is defined in the following. For any P also, let me any curve. So if I just did this, then I would just get an infinity metric. Right? If I define all lengths of all differential curves like this, I would get the infinity metric. And of course, the metric would be to take from it the distance from x to y is to go over all differentiable curves and take the infimum. So if I define lengths like this, it would just be the infinity metric. So the only thing here is that so this tries to capture the geometry of this. That the important thing about the geometry of that chain is that locally it doesn't matter where you are the body. Your geometry looks the same. So you have a cube, and all the adjacent cubes are of size either 1/2 or the same or twice. That's all. And this remains the same no matter where you are in the body. So, your steps become smaller and smaller in terms of real distance as you come close to the boundary. And this thing is supposed to capture that. No, that's not the thing. You're making progress. So you should measure that. And the way you measure that is by dividing by the distance, so that whatever is happening close to the boundary is similar to what is happening inside. That's what you want to capture. And so we have to prove the isoperimetric inequality for this. It turns out that proof goes into 2 parts. One part is to say that so you have this again, this S1, S2, S3 partitioning. If S1 has so take the smaller set S1, that's the one that is operative. A lot of its mass is well within the body. Then you are fine. Then this thing is essentially constant, far enough away from the body. Then you can just use any off the shelf. The interesting thing is what happens when most of it is actually very close to the boundary, and then you have to basically do localization by hand. So you integrate the thing in polar coordinates. You look at needles, which are you take a point instead of look at sort of break up the body into these needles while integrating in polar coordinates for each needle. So you say that because most of the mass is close to the boundary, said most of the mass is actually in needles which have most of so these good needles are also the one which have this property that most of the mass of the S1 set is close to the boundary. So then you see that most of the needles are actually good because most mass is in the boundary. And then for these needles, you again do a one-dimensional calculation, similar to the 1/T thing that we did. Of course, I don't want to make more enemies, so I can show it to you. Questions?
Let me ask, maybe I'm not fully, this doesn't make sense, but I thought even the needles would depend on the, like, I thought you would, rather than take actual intervals, you would do something like geodesics in this particular metric. Like the needles are not affected by the kind of distance.
Yes, they could be, and in principle, maybe by doing this, you could improve the isoperimetry. Well,
I mean, I thought the fact that that you were using the standard metric is why I thought you were using needles, and I thought the shape of the curves would change if the metric was different, but maybe.
yes, so in this case, it's somehow like, okay, so what I can say is about, so there's some isoperimetric inequality here that gives a conductance bound for the chain. That conductance bound is actually optimal for some sets. So it's not optimal for all sets. So in principle, there could be a way to improve it for some sets. So for cubes, it's actually optimal, like optimal up to log n factor. So there probably is not too much of an improvement in this. So I think the reason maybe it doesn't show up is like, I mean, so how will you do the arguments? You're looking at any one needle. You're anyway very close to the boundary. So all you can do is that it's sort of growing in this exponential or polynomial difference. So there's LT to the power n kind of the same phenomenon there, and that you want to exploit. And this does not really change whether you're doing on a straight line or so. There's the concavity of the distance is all that enters the picture, and then.
More questions?
And even in the coordinate hit and run, there's a different isoperimetric inequality underlying.
Yes, okay. So there the situation more complex. There is an isoperimetric inequality, which is the L0 distance. It's a strange. So it basically says something like this. If we have S1 and S2, says that if I just change one coordinate, I cannot get from S1 to S2. I have to change at least two coordinates to get from S1. Then whatever is left is large. That is needed. That is not by itself sufficient. Well, you first do it for the cube, then you try to, so cube you get something, and then you try to do it for the general body. So that's what they did. They did it by splitting the body. The way our proof works is you first have the conductors for this, and then you use that L0 for the cube, for the coordinate L0 for the cube, and the fact that this one has good conductance to do a comparison. Okay. So between the two. So it's not direct isoperimetry to conductance. It's a comparison argument for that. For this one, you can follow the same. So you take this isoperimetry, from that you get a conductance. So that calculation has to be done. That the isoperimetry for this implies conductance, but the intuition is exactly this. That this dividing by the distance is capturing the fact that even when you get close to the boundary, you're making progress at the same rate. But progress is measured by not wasted steps.
More questions? Not the case, so that's I don't know, there is some plans now, there are some plans now.
Yeah, so one is, I think one, so again, please check your emails regarding tomorrow excursions, whoever is joining. And there's still some more places. Some people want to join, just shoot us an email. Okay, and tomorrow night, for those who are staying at camp, there is no dinner at camp. So you have to find dinner elsewhere. Yeah, and the snacks now.
You can leave it.
Leave it.
You don't want any more damage.
Yeah,
no more damage.
No, but actually, I noticed that board actually has, I think, let's see, the two handles are broken.
Maybe did Piyush visit some time ago?
Maybe that was the previous time I did this.
They will clean it.
Really worried.
That was from the last visit.
No, he's worried his salary also will be deducted.
Fighting all this.
Yes,
I
really.
just thought you'd be very tired after 1.5 hours. I didn't want to go on.
It's not even
no ulterior motive.
It's not even the morning talk when it broke. It's like the late evening.
Huh? Yeah, like 1, 2, 3, 3 more handles.
Three
more dogs.
How many can you break?
which I would very much like to see. Last year for the elections, so that's very
some of us.
ratio. So I write to you and send you the.
It's a paper which is a very memorable, which was hidden and mixes fast.
Oh, okay, okay, I'll remember. Yeah, thanks a lot. Yeah. Mixes fast. Okay. Yeah, I hope you'll never forget that.
And the other one is hidden and
Oh, okay. Man, that's how you should write papers actually, so that nobody forgets the title.
Yeah, but he's not. I was actually a bit. I was a bit tired. Thanks. But the bus is there.
অলমোস্ট না না পুরো লেকচার না পুরোটাই
স্ক্যান করা নাকি
এটা স্যার আইপ্যাডে লিখতে
এই পুরোটা শেয়ার করে দিতে পারো চেক করে
হ্যাঁ সেটাই মনে হয় বেটার
কি আছে
ব্রাউনিয়ান মোশন শুধু ব্রাউনিয়ান মোশন
আরে পাঠিয়ে দিতে পারো
ব্রাউনিয়ান মোশন আমি তোকে তাহলে পাঠিয়ে দেবো
একটা করিয়েছিল ব্রাউনিয়ান সেখানে কোনো
করিয়েছিল কোথায় করিয়েছিল আমার মনে নেই ফাংশনাল সিএলটি ডেফিনেটলি করিয়েছিল আমাদের বুঝলাম আমাকে দেখতে হবে একবার বুঝলি দেখে আমি তোকে পাঠিয়ে দেবো সেটাই বেটার হবে হ্যাঁ হ্যাঁ তুই দেখে নিতে পারবি একই সাথে প্যারালালি এটাও চলছে ওইটা করতে হবে আমার এটা ক্রেডিট করতে হবে
করতে পারি কারণ আমাদের কম্পিটেন্সি বেশি ছিল আমার তবে কেউ না কেউ অফার করবে
এখন তো জাস্ট শেষ হয়েছে 1 মিনিট হলো শেষ হয়েছে 15 মিনিট পর ফোন না না করবো আমি বিকেল কেন করলি কেন তাহলে আর আমি 5 মিনিট পরে বলছি 5 মিনিট দাও 5 মিনিট
Joe is not there. He sent email and everything. Oh,
take all the The same, I think, Bollywood is also that's the same maybe I was there in the way of conference he asked which place and then he said they are happy. Happy about it. But Saga is also there. I know.
very excited. That's why I expert is not in that community.
Main road is something now. I road itself before the name of the place, but it is very close to about that. From about my road towards Saga no, for me the actual place is pretty close to all of the last one that you are brought up technical balance or you brought up or that is the third one is the only one is that you need to get so this is the longest like if you actually one of the longest letters you want to foreign you need a license not to sell yes, they are it's in the entire message there. Why was it wrong? The Indian is
a cost of and
no for hard we are Maharashtra is some of the strictest weirdest that I think they need to say like many of the songs have a more artistic effect. Yeah, that I don't know, like yeah. Yeah, always like a big I don't know.